Welcome, gentle friend, to our quiet journey. Take a soft, peaceful breath now, and allow yourself to settle into this space. A space where curiosity is allowed to unfurl slowly, like a delicate fern frond in the morning light. We're not here to rush, to solve, or to conquer. Instead, we're simply here to wonder, to explore the grand tapestries of the universe with a gentle mind, inviting contemplation rather than demanding answers. You see, the vastness of the cosmos isn't just a collection of facts, it's a silent symphony, a profound mystery that whispers to the very core of our being. And sometimes, in that quiet contemplation, we find a deep, unexpected sense of peace. Wherever you are listening from tonight, in whatever corner of the world, whatever time it may be for you right now, know that you are welcome here. We are, in this very moment, connected by this shared whisper of curiosity, a gentle bond across seconds and miles. I am so glad you are here. Tonight, we begin our quiet exploration by asking one of the most fundamental questions of all, a question that echoes through the deepest chambers of time and space. Where did it all begin? The universe, as we perceive it, is a tapestry of stars, galaxies, and perhaps even consciousness. Stretching further than our imagination can comfortably reach. But was there a moment, a singular point, from which everything sprang forth, or has existence always been? In some form or another, an endless, cyclical dance, the most widely accepted story. The grand narrative of our cosmic origins is the Big Bang Theory. Imagine, if you will, not an explosion in space, but an explosion of space itself. It's a subtle but crucial distinction, like stretching a balloon with dots on its surface. The dots move apart not because they're flying through the balloon, but because the balloon's surface itself is expanding. According to this theory, roughly 13.8 billion years ago, the entire observable universe was compressed into an incredibly hot, incredibly dense state, a singularity, smaller than the smallest atom, from this unimaginably compact point. Space and time themselves began to expand, cool, and evolve, giving birth to everything we see around us. Think of it as the ultimate cosmic sunrise, a moment when all of existence was born from an incandescent pinpoint, in the very first fractions of a second. The universe expanded at an astonishing, almost incomprehensible rate, a period known as cosmic inflation. This rapid expansion smoothed out any initial irregularities and stretched tiny quantum fluctuations to cosmic scales, planting the seeds for the large-scale structures we see today, like galaxies and galaxy clusters. It's a breathtaking thought, that the very fabric of reality could stretch so dramatically, in the blink of an eye, from something almost infinitely small to something vast beyond measure. As the universe continued to expand, it also cooled. And as it cooled, energy began to transform into matter in the earliest moments. Elementary particles like quarks and leptons formed. Then, as the cooling continued, these quarks combined to form protons and neutrons. For about the first 380,000 years, the universe was still too hot and dense for light to travel freely. It was a thick, opaque fog of plasma, where photons were constantly scattered by charged particles. This period is often likened to being inside a star, where light cannot escape. But then, as the universe continued its gentle expansion and cooled further, a pivotal moment arrived. The temperature dropped enough for electrons to combine with protons and helium nuclei, forming the first stable, neutral atoms. Suddenly, the universe became transparent. Photons were no longer constantly scattered, and light was free to travel through space. This ancient light, the earliest light we can detect, is known as the cosmic microwave background, CMB radiation. It's like a faint, ubiquitous glow, an ancient echo of the Big Bang, bathing the entire sky. When we look at the CMB, we are literally looking back in time to the universe's infancy, Witnessing the moment it became clear, like seeing the first gentle light break through a dense mist. This CMB radiation is one of the strongest pieces of evidence supporting the Big Bang theory. Its temperature, its remarkably uniform distribution across the sky, and the tiny fluctuations within it, all align beautifully with the predictions of the theory. It's a soft, pervasive hum throughout the cosmos, a lullaby from the dawn of time, telling us that our universe indeed had a fiery, dense beginning. After this moment of transparency, gravity, the quiet sculptor of the cosmos, began to work its magic. The tiny density fluctuations, those seeds planted during inflation, started to draw in more matter. Over hundreds of millions of years, these denser regions slowly coalesced, forming the first stars and then the first galaxies. These early stars, immense and short-lived, forged the heavier elements in their cores through nuclear fusion. Elements like carbon, oxygen, and iron, which are essential for life as we know it. When these giant stars reached the end of their lives, they exploded in spectacular supernovae, scattering these newly forged elements across the cosmos, enriching the interstellar medium with the building blocks of future stars, planets, and perhaps even ourselves. It's a beautiful thought that the very atoms in our bodies, the carbon in our bones, the oxygen in our breath that were once forged in the heart of distant, ancient stars, we are, quite literally, stardust. So, the Big Bang Theory paints a compelling picture, a universe born from an incredibly hot, dense state, expanding and cooling, forming light, then atoms, then stars, and finally galaxies, all unfolding over billions of years. It is a story of cosmic evolution, from simplicity to complexity, a grand unfolding drama. However, despite its immense success and the wealth of observational evidence, the Big Bang Theory, in its simplest form, still leaves us with some profound questions, questions that gently linger in the quiet corners of our minds. The most pressing among them is what happened before the Big Bang. If the Big Bang was the beginning of space and time, then the very concept of before becomes meaningless in our current framework. It's like asking what is north of the North Pole. Yet, our human intuition struggles with a true beginning, a moment when nothing became something. This question has led cosmologists to gently explore more speculative, yet deeply fascinating, ideas, pushing the boundaries of our understanding beyond the Big Bang itself. One such idea, as we briefly touched upon, is cosmic inflation. While inflation is often seen as a part of the Big Bang model, some interpretations suggest it might be a process that occurred not just once, but perpetually, leading to the concept of the multiverse. Imagine an eternally inflating superspace where inflation never truly ends, but rather continues in various regions, constantly spawning new bubble universes or pocket universes. Each of these bubbles would be a distinct universe, perhaps with its own unique set of physical laws and constants. Our Big Bang, in this view, would simply be the birth of one such bubble, one tiny corner of an unimaginably vast, eternally generating multiverse. It's a comforting thought for some, that existence isn't limited to our single cosmic bubble, but continues on in countless other forms, an infinite tapestry of realities. Another intriguing idea is the cyclic universe model. Instead of a single Big Bang followed by an eternal expansion, the Big Freeze. This model suggests that the universe undergoes an endless cycle of expansion and contraction. The universe expands, reaches a maximum size, and then begins to contract, eventually collapsing into a new Big Crunch. This Big Crunch then rebounds into a new Big Bang, restarting the cycle. It's a cosmic breathing, an endless inhale and exhale of existence, where our universe is just one phase in an eternal cosmic dance. This would mean there was no absolute beginning, just an infinite sequence of beginnings and endings, a timeless loop. Then there's the incredibly abstract and mind-bending concept of the no-boundary proposal, put forth by Stephen Hawking and James Hartley. This idea suggests that the universe didn't have a distinct beginning in time, in the way a clock starts ticking. Instead, it proposes that space-time itself, when traced back to its earliest moments, behaves like the south pole of the Earth. As you approach the South Pole, lines of longitude converge, and the concept of south loses its meaning. Similarly, as you go back in time towards the Big Bang, the universe's space-time rounds off in such a way that there is no sharp boundary or singular point where time truly began. It's a universe without a clear edge in time, a cosmos that simply is, without needing a before. This is a profoundly mathematical concept, and one that encourages us to let go of our intuitive, linear understanding of time, allowing for a more subtle, emergent view of its beginnings. These various theories and proposals are not mutually exclusive, and they represent humanity's persistent, quiet quest to understand its ultimate origins. They are the gentle whispers of science, reaching for truths that lie beyond our immediate perception, inviting us to contemplate the universe not just as a collection of observed phenomena, but as a deep, unfolding mystery. They remind us that the story of creation might be far more nuanced, more intricate, and more awe-inspiring than we can currently grasp. As we gently conclude this first chapter, allow your mind to drift with these profound questions about the universe's beginning. Ponder the incandescent pinpoint of the Big Bang, the endless creation of a multiverse, the cyclical breathing of a universe that never truly ends, or the elegant concept of a universe without a boundary. Feel the quiet awe of existing in a cosmos whose origins are still a wondrous mystery, inviting endless contemplation. There is a deep peace in this boundless uncertainty, in letting go of the need for definitive answers and simply embracing the universe's gentle, ever-unfolding story. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound narratives. Take another soft, peaceful breath now, allowing the mind-bending ideas of the Big Bang, eternal inflation, and a universe without a beginning to settle gently within your mind. We've just begun to explore the very genesis of everything, wondering about the incandescent spark that set existence into motion. Today, we will softly turn our gaze to a concept that intertwines with the beginning, yet also dictates the very fabric of our everyday experience, time itself. Imagine, for a moment, the relentless forward march of time. It feels so fundamental, so unyielding. We measure it with clocks, mark its passage with calendars, and feel its irreversible flow in every moment of our lives. The past is fixed, the present fleeting, and the future yet to unfold. This intuitive sense of time, flowing like a river, seems to be an undeniable truth of our existence. But what if time, in its deepest essence, is far more complex, more fluid, and even more mysterious than our everyday experience suggests? For centuries, time was largely considered by physicists to be an absolute, universal constant, ticking away uniformly for everyone, everywhere. Isaac Newton, the brilliant mind who described gravity, believed in an absolute time that existed independently of anything else, a kind of cosmic clock against which all events in the universe could be measured. In this view, time was the steadfast backdrop, unchanging and unyielding, against which the drama of the universe played out. However, the universe, in its gentle complexity, often delights in defying our simplest intuitions. Just as we've seen the vacuum reveal its dynamic nature, time, too, holds secrets far stranger and more active than mere linear progression suggest. The true revolution in our understanding of time came with Albert Einstein and his groundbreaking theories of relativity. First, his special theory of relativity, published in 1905, quietly shattered the notion of absolute time. Einstein proposed that time is not absolute but relative. This means that the passage of time can actually be different for different observers. Depending on their relative motion, imagine, if you will, two gentle travelers moving at very different speeds. For the traveler moving faster, time would actually slow down relative to the one moving slower. This phenomenon is called time dilation. It's not just an illusion, it's a real effect, a subtle stretching of time itself. While these effects are imperceptible at our everyday speeds, they become significant at speeds approaching the speed of light. For example, atomic clocks on satellites in orbit run slightly faster than identical clocks on Earth. A tiny difference that must be accounted for to ensure the accuracy of GPS systems. It's a quiet whisper from the cosmos, telling us that time is not a rigid backdrop, but a flexible, responsive element of reality. Then, in 1915, Einstein unveiled his general theory of relativity, which deepened this understanding even further. Intertwining time with space and gravity, he showed that time is not separate from space, but rather woven together with it into a unified, four-dimensional fabric called space-time. And here's the truly mind-bending part. Mass and energy can warp and curve this fabric of space-time. Imagine space-time, as we discussed in the context of gravity, as a vast, flexible sheet. A massive object, like a star, creates a dent in this sheet. This dent affects not only the paths of objects moving through space, but also the passage of time. The closer you are to a massive object, the more deeply you are embedded in its gravitational well, and the slower time will pass for you relative to someone further away. This is known as gravitational time dilation. For example, clocks at the top of a tall building run infinitesimally faster than clocks at its base. Because they are slightly further away from Earth's gravitational pull, it's a subtle, constant dance between mass, space, and time, revealing that time's flow is not uniform, but a gentle curve influenced by the very presence of matter and energy. These revelations fundamentally changed our understanding. Time is not an independent entity. It is inextricably linked to space and to the presence of mass and energy. It is a dynamic, elastic dimension, capable of stretching, compressing, and bending, influenced by the very things within the universe. It's a beautiful, intricate ballet where every cosmic dancer, from a tiny particle to a colossal galaxy, subtly affects the rhythm of time around it. This leads us to a more profound philosophical question. If time is so flexible, why do we only ever experience it flowing in one direction from past to present to future? Why is there an arrow of time? The fundamental laws of physics, at the microscopic level, are largely time-symmetric. They work just as well if time is run backward. For example, a video of billiard balls colliding would look perfectly normal if played in reverse. Yet, in our macroscopic world, time's arrow is undeniably unidirectional. We remember the past, but not the future. Spilled milk doesn't spontaneously gather back into a glass. Broken objects don't reassemble themselves. One leading explanation for the arrow of time comes from the concept of entropy, which we briefly touched upon when considering the universe's end. Entropy is a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system can only increase over time, or at best, remain constant. It never decreases. Things naturally move from order to disorder. Your room tends to get messy, not spontaneously tidy itself. The universe, too, is constantly increasing its overall disorder. The Big Bang started the universe in a state of incredibly low entropy, highly ordered and compact. As the universe expands and evolves, its entropy constantly increases. This continuous increase in entropy might be the fundamental reason we perceive time as flowing in only one direction. It's a quiet reminder that the universe itself is always gently moving towards a state of greater dispersal, greater uniformity, a gradual unfolding into wider possibilities. But what if, as we briefly explored in Chapter 16, the future already exists, or in some way influences the past? This is the realm of the block universe theory, which takes Einstein's space-time framework to its logical conclusion. In the block universe, all of time past, present, and future exists simultaneously as a fixed, four-dimensional continuum. Our perception of time flowing or a now moving forward is simply our consciousness moving through this pre-existing block. Every moment, every event, from the birth of the first star to the heat death of the universe, is eternally present within this cosmic block, like frames in a film reel that all exist at once. Even though we only perceive them one by one, this concept can be deeply unsettling to our intuitive sense of free will and choice. If the future is already set within the block, are our decisions merely illusions? This is a question that gently nudges against the very fabric of our subjective experience. However, it can also be a source of profound calm. In a block universe, nothing is truly lost. Every cherished memory, every fleeting moment of joy, every whisper of love is eternally preserved, not as a fading echo, but as a real, fixed point within the timeless cosmic whole. It suggests a universe of perfect completeness, where every story, every melody, has already been written into the very fabric of existence. And what about the very beginning of time if the Big Bang was the start of space-time? Then what about the nothingness before it, or if, as the no-boundary proposal suggests? Space-time simply rounds off without a sharp beginning. How do we reconcile that with our need for a clear point of origin? These are the questions that continue to gently push the boundaries of our understanding, inviting us to reconsider our most fundamental assumptions. Perhaps time is not just a linear river, but a vast ocean, with currents and eddies, some flowing forward, some perhaps even subtly influencing what came before. Perhaps our perception of time is merely a localized phenomenon, specific to our particular corner of the cosmos, or to the way our conscious minds process information. The deeper we delve into the nature of time, the more it seems to dissolve into something far more abstract and integrated with the very essence of reality itself. It's a profound thought that the very now we inhabit is not just a fleeting moment, but a point within an eternal, interconnected cosmic tapestry. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes unsettling ideas about time. Ponder its relativity, its intimate connection to gravity, its relentless arrow of increasing disorder, or its eternal presence in a block universe. Feel the quiet awe of existing in a cosmos where time is not just a given, but a dynamic, mysterious dimension, inviting endless contemplation. There is a deep peace in this boundless uncertainty, in letting go of rigid notions of temporal flow and embracing the universe's gentle, ever-unfolding story. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound narratives. Take another soft, peaceful breath now, allowing the mind-bending ideas of time's elasticity, its arrow of entropy, and its potential eternal presence within a block universe to settle gently within your mind. We've just explored how time, far from being a simple linear flow, is a dynamic and mysterious dimension, intimately woven into the fabric of reality itself. Today, we will softly turn our gaze to another fundamental aspect of our existence, one that often feels both incredibly solid and yet remarkably elusive matter. Imagine, for a moment, everything around you: the chair you might be sitting on, the air you breathe, the gentle light filtering through your window, and even your own hand resting softly. All of this, in our everyday experience, feels substantial, tangible, real. We perceive it as matter, something that takes up space and has mass. But what if the deeper truth about matter is far more nuanced, more ephemeral, and in some ways, more akin to patterns of energy or information than to tiny, hard, indivisible bits of stuff? For centuries, the prevailing view, dating back to ancient Greek philosophers, was that matter was composed of tiny, fundamental, indivisible particles, atoms. These atoms were thought to be the ultimate building blocks, immutable and eternal. In this classical view, the universe was like a vast collection of tiny, billiard ball-like particles, endlessly colliding and rearranging themselves to form everything we see. It was a comforting, predictable universe built from solid, tiny components. However, the universe, in its gentle complexity, often delights in defying our simplest intuitions. The early 20th century, with the dawn of quantum mechanics, quietly shattered this simple picture. We discovered that atoms were not indivisible. They were made of even smaller particles, a nucleus at the center, composed of protons and neutrons, surrounded by orbiting electrons. But the revelations didn't stop there. Protons and neutrons themselves were found to be made of even tinier, more fundamental particles called quarks. And then came the perplexing discovery that these particles, at the quantum level, don't behave like tiny, solid billiard balls at all. They exhibit a strange, dual nature, sometimes acting like discrete particles, sometimes spreading out like waves. This wave-particle duality is one of the most mind-bending aspects of quantum mechanics, suggesting that matter, at its most fundamental level, is not as solid or definite as we perceive it to be. It's more like a probability wave, a potentiality that only collapses into a definite particle when observed. Think of it like a whisper in the dark. Before you turn on the light, the whisper could be coming from anywhere in the room. It's a distributed presence, a wave of sound. But the moment you shine a light and focus, the sound localizes to a specific point, a particle-like source. Similarly, a quantum particle exists as a blur of possibilities, a wave of potential, until the act of measurement or observation gently nudges it into a definite state. This means that our very act of looking, of interacting with reality, seems to play a role in defining what matter truly is at this fundamental level. This leads us to the standard model of particle physics, our current best understanding of the fundamental building blocks of matter and the forces that govern them. It's a beautiful, intricate tapestry that classifies all known elementary particles into two main groups: fermions, which are the matter particles, and bosons, which are the force-carrying particles. The fermions include the quarks, which make up protons and neutrons, and leptons, which include electrons, muons, and neutrinos. These are the stuff of the universe, the particles that make up all the atoms and ultimately all the familiar matter around us. They are the intricate notes in the cosmic melody. The bosons are the particles that mediate the fundamental forces. The photon carries the electromagnetic force responsible for light, electricity, and magnetism. The gluon carries the strong nuclear force which binds quarks together to form protons and neutrons, and holds the nucleus of an atom together. The W and Z bosons carry the weak nuclear force responsible for radioactive decay and nuclear fusion in stars, and most famously in recent years, the Higgs boson, which is associated with the Higgs field, is thought to give other particles their mass. It's a subtle, pervasive field, like a cosmic molasses, through which particles move, acquiring their mass as they interact with it. So, in the standard model, matter isn't just one thing. It's a rich zoo of different particles, each with its own unique properties, constantly interacting through the exchange of force-carrying particles. It's an incredibly successful theory, having predicted the existence of many particles before they were experimentally discovered, including the elusive Higgs boson. It's like a grand, meticulously constructed clockwork, where every gear and spring plays its crucial role in the cosmic mechanism. However, the universe, in its boundless mystery, still holds secrets that extend beyond the standard model. For one, the standard model does not include gravity, while it beautifully describes the other three fundamental forces. Gravity. as described by Einstein's general relativity, remains stubbornly separate, the quest to find a quantum particle for gravity. The graviton, and to reconcile these two pillars of physics into a unified theory of everything, is one of the deepest challenges in modern physics. A quiet whisper from the universe inviting us to delve deeper into its fundamental nature. Furthermore, the matter we observe, the protons, neutrons, and electrons that make up stars, planets, and ourselves, accounts for only about 5% of the universe's total mass energy content. The vast majority of the cosmos is made of something we cannot see, something that does not interact with light dark matter and dark energy. Dark matter, accounting for about 27% of the universe, is a mysterious substance that does not emit, absorb, or reflect light, making it invisible to our telescopes. However, we know it's there because of its gravitational effects on visible matter. Galaxies rotate faster than they should if they only contained the visible matter we can see, and galaxy clusters are held together by more gravity than their visible components can provide. Dark matter is the silent, unseen scaffolding that holds the cosmic web together, a ghostly presence that hints at a universe far richer than our eyes can perceive. It's a profound thought that most of the matter in the universe is something utterly alien to our everyday experience, something that drifts through us without ever touching or interacting. Dark energy, which makes up about 68% of the universe, is an even greater enigma. It is the mysterious force that is accelerating the universe's expansion, pushing galaxies further and further apart. It's as if empty space itself has an intrinsic, repulsive energy, causing the cosmos to inflate at an ever-increasing rate. Dark energy is the quiet, pervasive force shaping the ultimate destiny of the universe, a subtle hum that dictates the grand cosmic ballet. So, when we speak of matter, we are often referring to only a tiny fraction of what actually exists in the universe. Most of the cosmos is composed of unseen, unknown entities, hinting that our understanding of reality's fundamental constituents is still very much in its infancy. It's a humbling thought that, despite our incredible scientific progress, the vast majority of existence remains a profound mystery, a quiet invitation to continue our exploration. This journey into the nature of matter also gently touches upon our earlier discussions of information. If quantum particles are not solid bits, but probability waves that resolve into definite states upon observation, does that imply that information itself is more fundamental than matter is the universe? At its deepest level, truly an it-from-bit scenario, where physical reality emerges from patterns of information. These are the profound questions that linger, inviting us to contemplate a universe where the lines between matter, energy, and information begin to blur, dissolving into a more unified, elegant, and mysterious whole. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes counterintuitive ideas about matter. Ponder the vibrant dance of quantum particles, the unseen scaffolding of dark matter, and the elusive force of dark energy. Feel the quiet awe of existing in a cosmos where stuff is far stranger and more ephemeral than it seems. Inviting endless contemplation, there is a deep peace in this boundless mystery, in letting go of rigid definitions of what is real and embracing the universe's gentle, intricate nature. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound narratives. Take another soft, peaceful breath now, allowing the mind-bending ideas of matter's elusive nature, its quantum dance, and the mysteries of dark matter and dark energy to settle gently within your mind. We've just explored how the tangible world around us is, at its deepest level, a vibrant interplay of energy and probability, with much of the cosmos remaining unseen. Today, we will softly turn our gaze to a concept that underpins all these interactions, holding everything together while allowing for all the dynamism and change forces and fields. Imagine, for a moment, the hidden hands that orchestrate the cosmic ballet. What makes planets orbit stars? What binds atoms together? What causes light to travel? And what fuels the very sun that warms our skin? These are all manifestations of fundamental forces, invisible influences that permeate the universe, shaping its structure and driving its evolution. For centuries, these forces were often thought of as simple pushes or pulls, distinct and separate, but the universe, in its gentle complexity, often delights in revealing deeper, more unified truths. Our modern understanding suggests that these fundamental forces are not just mysterious pulls, but are mediated by fields. Imagine a field as an invisible influence that fills space, like an ocean of potential. When you drop a stone into water, ripples spread out. Similarly, when a particle exists in a field, it creates a disturbance or an excitation in that field. And this disturbance is what we perceive as a force. At the quantum level, these fields are not continuous, they are quantized, meaning their energy exists in discrete packets called force-carrying particles, or bosons. These bosons are the tiny, ephemeral messengers that transmit the forces between matter particles. The standard model of particle physics, which we touched upon, beautifully describes four fundamental forces that govern all interactions in the universe. Let's gently explore each of them. First, there is the strong nuclear force. This is the most powerful of all the forces, but its reach is incredibly short. Confined to the nucleus of an atom, imagine it as a tiny, immensely powerful glue. This force is carried by particles called gluons, which constantly bind quarks together to form protons and neutrons. Without the strong force, protons, which carry positive charges and naturally repel each other, would simply fly apart, and atomic nuclei could not exist. Our entire world, built from atoms, would instantly disintegrate. It's a profound thought, the very solidity of everything around us. The gentle ground beneath our feet, the warmth of a fire, is held together by this powerful, hidden force, acting at unimaginably tiny scales. The strong force is the silent, steadfast anchor of the atomic world. Next, we have the electromagnetic force. This is the force we are perhaps most familiar with in our everyday lives. It's carried by the photon, the particle of light. The electromagnetic force is responsible for all light, electricity, magnetism, and chemistry. It's what binds electrons to atomic nuclei, allowing atoms to form molecules. It dictates how light interacts with matter, giving rise to all the colors we perceive. It's the force that allows your eyes to see, your phone to work, and magnets to stick to your fridge. It is much weaker than the strong force, but its range is infinite. Imagine it as a vast, energetic dance where charged particles constantly exchange photons, feeling each other's influence across vast distances. The electromagnetic force is the vibrant, luminous sculptor of chemistry and light, shaping the visible universe around us. Then there is the weak nuclear force. This force is responsible for certain types of radioactive decay, a process where unstable atomic nuclei transform into different elements. It's carried by the W and Z bosons. While not as intuitive as the other forces, the weak force plays a crucial role in powering stars. In the sun's core, the weak force is involved in the nuclear fusion reactions that convert hydrogen into helium, releasing the immense energy that reaches us as sunlight and warmth. It's a subtle but vital force, a quiet alchemist transforming elements and fueling the cosmic furnaces. And finally, there is gravity. We dedicated a whole chapter to this grand architect, but it's essential to reiterate its role as one of the fundamental forces. As we explored, Einstein's general relativity reimagined gravity not as a force in the traditional sense, but as the curvature of spacetime caused by mass and energy. However, in the quest for a unified theory, physicists still seek to describe gravity at the quantum level, where it would be mediated by a force-carrying particle called the graviton, if found. The graviton would be the quantum messenger of spacetime's curvature, constantly exchanging information about mass and energy, gently pulling everything together. Gravity is by far the weakest of the four fundamental forces, but its range is infinite, and it is always attractive. This means that on cosmic scales, gravity dominates, shaping galaxies, forming stars, and dictating the large-scale structure of the universe. It's the gentle, pervasive embrace that holds the cosmos together. So, we have these four fundamental forces, the incredibly strong but short-range strong nuclear force holding atomic nuclei together, the pervasive electromagnetic force responsible for light and chemistry, the subtle weak nuclear force involved in radioactive decay and stellar fusion, and the universally attractive gravity. Shaping the cosmos on the largest scales, each plays a distinct yet interconnected role in the universe's grand design. But the story of forces and fields doesn't end there. For decades, physicists have harbored a profound dream to unify these forces into a single, elegant theory. This dream is often called the quest for a theory of everything. The first successful step was the unification of the electromagnetic and weak forces into the electro-weak force at high energies, a triumph confirmed by experiments at particle accelerators. This showed that what appear to be separate forces at everyday energies can actually be different manifestations of a single, more fundamental force at higher energies, like different facets of a single shimmering jewel. The next step is to unify the electroweak force with the strong nuclear force into a grand unified theory gut. Many theoretical frameworks exist for guts, but none have yet been definitively proven by experiment. And the ultimate challenge, the holy grail of physics, is to then incorporate gravity into this framework, creating a single coherent theory that describes all fundamental forces and particles in the universe. This pursuit of unification is a profound reflection of humanity's quiet longing for simplicity and elegance in the face of cosmic complexity. It's a belief that beneath the apparent diversity of forces, there lies a deeper, more beautiful unity, a single, overarching principle that governs all of reality. The concepts of forces and fields also subtly intertwine with our discussions of the quantum vacuum. Remember, the quantum vacuum is not empty, it is a bustling sea of virtual particles. These virtual particles are constantly popping into and out of existence, exchanging energy, and mediating the very forces we experience. It's as if the empty space between particles is not truly empty, but filled with the silent whispers of these force-carrying particles, constantly relaying information and enabling interactions. This means that the forces we perceive are not just abstract pulls, but dynamic, energetic processes constantly unfolding in the very fabric of space-time. Think of it as a vast, invisible orchestra, where each field is an instrument, and the force-carrying particles are the notes, constantly playing the cosmic symphony, from the tiniest atom held together by the strong force to the grand galaxies dancing under gravity's pull. Everything is part of this intricate, energetic composition, and our role, as curious observers, is to gently listen, to try and discern the patterns, and to appreciate the profound beauty of these hidden orchestrations. As we gently conclude this chapter, allow your mind to drift with these profound ideas about forces and fields. Ponder the invisible glue that binds the atom, the vibrant energy that powers light, the subtle decay that fuels the stars, and the grand embrace that shapes the galaxies. Feel the quiet awe of existing in a cosmos where everything is interconnected by these fundamental influences. A universe constantly humming with unseen energy and silent communication. There is a deep peace in this boundless mystery, in letting go of rigid definitions of separateness and embracing the universe's gentle, unified dance. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound narratives. Take another soft, peaceful breath now, allowing the intricate dance of fundamental forces and fields, holding all of reality together, to settle gently within your mind. We've explored how seemingly separate pulls and pushes are, at a deeper level, mediated by invisible energies and messenger particles, creating the very fabric of interaction. Today, we will softly turn our gaze inward, to the most intimate and baffling mystery of all consciousness. Imagine, for a moment, the simple act of experiencing, the warmth of sunlight on your skin, the subtle scent of rain, the gentle hum of quiet in the room, the thoughts and feelings swirling within your own mind. This entire subjective landscape, this vibrant inner world, is what we call consciousness. It is, perhaps, the only thing we know with absolute certainty, the very act of knowing. And yet, despite its immediacy, it remains one of the most elusive and profound puzzles in all of science and philosophy. What exactly is consciousness? Is it merely a complex output of our brains? A highly sophisticated biological computer at work? Or is it something more? Something fundamental? A property woven into the very fabric of the cosmos itself? This is the hard problem of consciousness. Coined by philosopher David Chalmers, how do physical processes in the brain give rise to subjective experience? To the feeling of what it's like to be you. We can map brain activity, identify neural correlations, but explaining why those activities produce a conscious experience, rather than just processing information, remains a profound mystery. Think of it like this. We can understand how a computer works, how electricity flows through its circuits, how algorithms process data, but this understanding doesn't explain the experience of seeing the image on the screen, or feeling the warmth of the device. Consciousness seems to be a leap beyond mere computation, a qualitative leap into subjective awareness. One leading scientific perspective suggests that consciousness emerges from the complex interactions of billions of neurons in the brain. Our brain, with its intricate networks and electrochemical signals, is an incredibly sophisticated organ, perhaps the most complex structure known in the universe. As neurons fire and connect in specific patterns, they somehow give rise to thoughts, emotions, perceptions, and the sense of self. It's an emergent property, much like wetness emerges from the interaction of water molecules, even though individual water molecules aren't wet in this view. Consciousness is a highly complex phenomenon that arises from simpler components. A beautiful, intricate symphony played by the brain's vast orchestra. This perspective implies that consciousness is tied specifically to biological complexity. If so, then perhaps only creatures with sufficiently complex brains, like humans and certain animals, possess consciousness. And if we could build an artificial intelligence that perfectly replicated the neural network of a human brain, then it, too, might become conscious. This is a profound and perhaps unsettling thought, pushing us to consider the ethical implications of creating truly sentient machines. However, other theories gently push back against this purely emergent, brain-centric view, suggesting that consciousness might be more pervasive, more fundamental than we often assume. One such idea is panpsychism. Imagine, if you will, that consciousness, or at least proto-consciousness, a very basic form of experience or awareness, is not limited to complex brains, but is a fundamental property of matter itself, or at least exists at the most basic levels of reality. It's not that every atom or particle is conscious in the way a human is, but that they possess some infinitesimal, rudimentary capacity for experience. Just as mass or charge is a fundamental property of particles, so too might be a tiny glimmer of awareness. In this view, the hard problem of consciousness might be rephrased instead of asking how consciousness emerges from unconscious matter. We ask how these tiny, fundamental bits of proto-consciousness combine and integrate to form the complex, unified consciousness we experience as humans. It's like asking how individual musical notes, each simple in itself, combine to form a complex, rich symphony. This perspective suggests that the universe itself, at its deepest level, might be infused with a subtle form of awareness, a quiet hum of proto-experience that permeates everything. This idea can be deeply calming. If consciousness is fundamental, it means that awareness isn't a fragile, fleeting byproduct of biological processes, but an intrinsic aspect of existence. It hints at a universe that is not merely a collection of inert particles, but a living, experiencing entity. In some profound, unknowable way, it connects us, our inner world, to the very fabric of the cosmos, making us not just observers of the universe, but expressions of its inherent awareness. Beyond these views, some theories explore the connection between consciousness and the strange rules of quantum mechanics. The act of observation in quantum mechanics, where a particle's probability wave collapses into a definite state, has led some to speculate about the role of consciousness in shaping reality. Is consciousness somehow involved in this collapse? Does the act of awareness somehow influence the quantum realm? While this remains a highly speculative and debated area, it highlights the profound implications if consciousness were found to be entangled with the fundamental laws of the universe. It's a gentle whisper from the quantum realm, suggesting that the line between observer and observed might be far more blurred than we imagine. Another intriguing question that arises is the nature of self-awareness. Many creatures have a form of awareness, responding to stimuli and navigating their environments. But humans, and perhaps a few other species, possess the ability to reflect on their own thoughts, to ponder their own existence, to ask, "Who am I?" This meta-awareness, this inner monologue and sense of a continuous self, adds another layer of complexity to the mystery of consciousness. Is it a unique product of our evolved brains, or a deeper, more profound capability that could manifest in other forms across the cosmos? The study of consciousness also touches upon the mystery of free will. If our brains are physical systems governed by physical laws, are our choices predetermined, or does consciousness, with its subjective experience, allow for a genuine capacity for choice, for genuine agency in the unfolding of events? This profound philosophical debate is intimately linked to how we understand the nature of consciousness itself. It's a quiet tension between the deterministic dance of particles and the subjective feeling of making a decision. As we continue to explore the cosmos, the more we discover about the intricate workings of the brain, the more questions arise about consciousness. Neuroscientists map neural pathways, psychologists study cognitive processes, and philosophers wrestle with the conceptual challenges. Yet, the hard problem persists, a gentle reminder of the universe's ultimate mystery, residing not just in distant galaxies, but within the very core of our own being. Perhaps consciousness is not something we have, but something we are. Perhaps it is the universe experiencing itself, a fleeting, precious manifestation of cosmic awareness. It's a humbling thought that our individual consciousness, with all its thoughts, feelings, and dreams, is intimately connected to the grand tapestry of existence, a tiny, luminous thread in the boundless fabric of awareness. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes unsettling ideas about consciousness. Ponder its elusive nature, its potential emergence from complexity, its possible pervasiveness throughout the cosmos, or its entanglement with the quantum realm. Feel the quiet awe of existing as a conscious being, a luminous point of awareness in a vast, mysterious universe, inviting endless contemplation. There is a deep peace in this boundless mystery, in letting go of rigid definitions of what it means to be and embracing the universe's gentle, self-aware unfolding. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound narratives. Take another soft, peaceful breath now, allowing the elusive nature of consciousness, its potential emergence or pervasive presence, to settle gently within your mind. We've just explored how the very act of experiencing remains a deep mystery, perhaps connecting us to the cosmos in ways we are only beginning to fathom. Today, we will softly turn our gaze outward again, to the grand stage upon which all these mysteries unfold, the vastness of space. Imagine, for a moment, the sheer, unimaginable scale of it all. When we look up at the night sky, we see a scattering of stars, a luminous dust against the inky blackness. Each tiny point of light, if visible to the naked eye, is a sun, often far grander than our own, burning brightly billions of miles away. But this visible tapestry is merely the thinnest veil over an abyss of unimaginable dimensions, a profound emptiness that is anything but empty. Our intuitive sense of space is three-dimensional length, width, and height. We move through it effortlessly in our daily lives, but the universe's space is not merely a static, empty stage. It is dynamic, ever-expanding, and filled with a hidden architecture that dictates the dance of galaxies and the very limits of our perception. Let's begin our gentle journey outward. Starting from our immediate cosmic neighborhood, our Earth is a tiny, precious blue marble, orbiting a modest star we call the Sun. Our Sun is just one of hundreds of billions of stars in our Milky Way galaxy. Imagine a colossal spiral, a majestic cosmic pinwheel, spanning roughly 100,000 light-years across. A light year, a term we'll use often, is the distance light travels in 1 year, an astounding 5.88 trillion miles, or 9.46 trillion kilometers. So, our galaxy is truly immense. Taking light 100,000 years to cross from one edge to the other, our Sun is nestled about 2/3 of the way out from the galactic center, in one of its spiral arms, quietly completing an orbit around the galactic core every 240 million years. This means the last time our solar system was in this position in the galaxy, dinosaurs roamed the Earth. It's a humbling thought that our home is merely a tiny speck, gently orbiting within this grand, swirling vortex of stars. But the Milky Way is not alone. It is part of a larger cosmic structure, a gravitational embrace with its nearest galactic neighbors. Our closest large galactic twin is the Andromeda Galaxy, a majestic spiral even larger than our own, located about 2.5 million light-years away. Andromeda is hurtling towards the Milky Way at an astounding speed, and in about 4.5 billion years. These two colossal galaxies are destined to gently merge, a slow-motion cosmic dance that will transform both into a new, larger elliptical galaxy. It's a profound thought that our galactic home is on a collision course, not a violent crash, but a graceful, billions of years long embrace with its closest cosmic companion. Our Milky Way and Andromeda, along with dozens of smaller dwarf galaxies, form a gravitationally bound group known as the local group. This local group is itself merely a tiny cluster within an even larger cosmic tapestry. These galaxy groups and clusters are not randomly scattered. They are arranged in vast, filamentary structures, like a colossal cosmic web. Imagine long, luminous threads of galaxies stretching across billions of light-years, interspersed with immense, dark voids. This is the large-scale structure of the universe, a frothy web-like pattern that speaks to the gravitational sculpting of matter over cosmic time. The largest known structure we've identified is the Laniakea supercluster, an unimaginably vast collection of about 100,000 galaxies, including our own local group, all slowly drifting towards a common gravitational center called the Great Attractor. This supercluster spans an incredible 520 million light-years across. It is humbling to consider that our entire galactic neighborhood, with its hundreds of billions of stars, is just a small component of this larger, slowly moving river of galaxies. And beyond these superclusters, more filaments, more voids, stretching out in every direction. As far as our most powerful telescopes can peer, the observable universe, the part of the cosmos from which light has had time to reach us since the Big Bang, has a diameter of roughly 93 billion light-years. That's a staggering number, almost impossible for our minds to fully grasp. It represents the limit of what we can currently see. A luminous sphere centered on us, expanding with the universe itself. But what about the space beyond the observable universe? We don't know for certain. But theoretical models suggest that the universe is likely far, far larger than what we can observe. Possibly infinite. Our observable universe might just be a tiny, luminous bubble within an unimaginably vaster, perhaps infinite, cosmos. It's a profound thought. The boundaries of our perception are not necessarily the boundaries of existence itself. The vastness of space is not merely empty distance. It is permeated by the cosmic microwave background, CMB radiation, the ancient echo of the Big Bang, bathing the entire sky in a uniform, gentle glow. It is also filled with the invisible, elusive presence of dark matter, the mysterious substance that provides the gravitational scaffolding for galaxies and galaxy clusters, pulling them together and preventing them from flying apart. And permeating every inch of this vastness is dark energy, the even more enigmatic force that is accelerating the universe's expansion, pushing galaxies further and further apart, dictating the ultimate fate of the cosmos. So, what appears as empty space is, in fact, a dynamic, energetic medium, filled with unseen influences and ancient whispers. The expansion of space itself is perhaps the most profound aspect of its vastness. The universe is not just expanding into something, space itself is stretching, carrying galaxies along with it, like raisins embedded in an expanding dough. This expansion means that the further away galaxies are, the faster they appear to recede from us, a phenomenon known as Hubble's law, and the surprising discovery that this expansion is accelerating, driven by dark energy, adds another layer of mystery to the very nature of space. It suggests that space is not just a container, it has its own inherent energy, its own cosmic pressure that gently pushes everything apart as we quietly contemplate this boundless expanse. The vastness of space can evoke a profound sense of both humility and wonder. Humility, because it reminds us of our own minuscule place within this grand, cosmic tapestry. Wonder, because it reveals a universe of breathtaking scale, intricate structure, and hidden energies. It's a space that is not static, but alive, constantly evolving, stretching, and perhaps endlessly generating. The quiet, gentle nature of this vastness invites us to let go of our everyday concerns and simply be present with the grandeur of it all. To imagine light traveling for billions of years to reach our eyes, carrying stories from the deepest past, to ponder the unseen forces that sculpt galaxies into their majestic forms, to feel the subtle stretch of space itself, carrying us gently into an unknown future. There is a deep peace in this boundless expanse, a quiet invitation to surrender to the scale of existence. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes overwhelming ideas about the vastness of space. Ponder the immense spirals of galaxies, the cosmic web of clusters and voids, and the unimaginable distances stretching beyond our sight. Feel the quiet awe of existing within a cosmos that is ever expanding, filled with unseen energies and constantly evolving, inviting endless contemplation. There is a deep peace in this boundless mystery, in letting go of rigid definitions of limits and embracing the universe's gentle, infinite unfolding. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound narratives. Take another soft, peaceful breath now, allowing the unimaginable vastness of space, its accelerating expansion, and the hidden presence of dark matter and dark energy to settle gently within your mind. We've just explored how the cosmic stage itself is a dynamic, evolving entity filled with unseen influences. Today, we will softly turn our gaze to something even more elusive and mind-bending, a concept that challenges our very definition of nothingness, the quantum vacuum. Imagine, for a moment, what you perceive as empty space, the space between the stars, the space within an atom, the quiet void that seems to stretch endlessly. Our intuition tells us that empty means truly nothing, a perfect void, devoid of any activity, any substance, any energy. For centuries, this was largely the prevailing view. Space was simply a passive container, a backdrop for matter and energy. However, the universe, in its gentle complexity, often delights in defying our simplest intuitions. The quantum revolution of the 20th century quietly shattered this classical notion of emptiness. Modern physics tells us that empty space is anything but empty. In fact, it's a teeming, bubbling cauldron of activity, a vibrant sea of potential, even at the lowest possible energy state. This is the profound concept of the quantum vacuum. Think of it not as a passive void, but as a vast, invisible ocean of energy, a universal background field that permeates every corner of the cosmos. According to quantum field theory, even in the deepest vacuum, where there are no particles or photons present, there are continuous, fleeting fluctuations in the energy fields that fill space. These fluctuations are so vigorous that virtual particles are constantly popping into and out of existence, seemingly out of nowhere and then vanishing almost instantly. Imagine, if you will, the surface of a perfectly still pond. Our classical intuition expects it to remain perfectly flat and undisturbed. But if you were to look at it through a very powerful, quantum-sensitive microscope, you would see that even in its stillness, the surface is constantly rippling and bubbling with tiny, ephemeral waves, appearing and disappearing in an instant. These tiny, fleeting ripples are analogous to the virtual particles of the quantum vacuum. They are pairs of particles and their corresponding antiparticles like an electron and a positron, or a photon and an antiphoton that spontaneously appear, exist for an infinitesimally short period dictated by the Heisenberg uncertainty principle, and then annihilate each other, returning their energy to the vacuum. This isn't just a theoretical fancy. These quantum fluctuations have measurable effects. For instance, the Casimir effect provides experimental evidence for the reality of these virtual particles. If you place two uncharged, perfectly parallel metal plates very close together in a vacuum, a tiny attractive force arises between them. This force is explained by the fact that the virtual particles outside the plates can have any wavelength, but those between the plates are restricted to wavelengths that fit exactly within the tiny gap. This leads to slightly fewer virtual particles, and thus less energy, between the plates than outside, creating a net inward pressure that gently pushes the plates together. It's a subtle, almost imperceptible whisper from the quantum vacuum, demonstrating its very real, energetic presence. The quantum vacuum is also intimately connected to the concept of the Higgs field, which we touched upon when discussing matter. The Higgs field permeates all of space. Its constant interaction with elementary particles gives them mass. Without the Higgs field, particles would be massless, hurtling through the universe at the speed of light, and atoms as we know them could not exist. The quantum vacuum is the lowest energy state of this Higgs field, still humming with activity, still subtly interacting with everything. It's like a cosmic molasses, present everywhere, constantly influencing the very solidity of matter. This vibrant, energetic nature of the quantum vacuum has profound implications for our understanding of reality, and even for the very origin of the universe. If empty space is truly a boundless reservoir of potential energy, could it be the ultimate source of everything? Some speculative theories suggest that the universe itself, with all its matter, energy, and space-time, could have tunneled out of the quantum vacuum in an act of cosmic creation. It's as if a tiny fluctuation, an infinitesimally improbable bubble of energy, suddenly expanded and inflated, becoming our universe. This would mean that the universe didn't emerge from absolute nothingness, but from the dynamic, pregnant nothingness of the quantum vacuum. Consider also the idea of inflation, which we discussed in the context of the Big Bang. Cosmic inflation, the incredibly rapid expansion of the universe in its earliest moments, is thought to have been driven by an energy field that temporarily dominated the universe. Perhaps an inflatoned field that released its energy into the vacuum. This suggests that the vacuum itself can harbor immense amounts of energy. Capable of shaping the entire cosmos, the quantum vacuum also challenges our notions of locality. If virtual particles are constantly popping into and out of existence, sharing their energy with the vacuum, does this imply a deeper interconnectedness across space, the universe? At its most fundamental level, seems to be a unified, vibrating whole, where even the empty spaces are alive with subtle energy and constant interaction. It's a gentle reminder that even in apparent stillness, there is boundless activity, an unceasing dance of creation and annihilation. This concept can be deeply calming. If the vacuum, the nothingness, is teeming with potential, then perhaps moments of quiet, moments of emptiness in our own lives, are also not truly empty. Perhaps they are pregnant with possibility, brimming with unseen energies and nascent creations, waiting to unfold. It suggests that even in moments of profound stillness, there is a vibrant, unseen life, a profound connection to the universal hum. The quantum vacuum is a subtle, almost poetic concept, inviting us to reconsider our assumptions about reality. It tells us that the universe is far richer and more intricate than our senses typically perceive. It reminds us that nothing is not truly empty, but a vibrant canvas of potential, constantly giving birth to and reclaiming existence. It's a profound thought. The very space we inhabit, the seeming void between our fingers, is a shimmering sea of quantum possibilities. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes counterintuitive ideas about the quantum vacuum. Ponder the constant dance of virtual particles, the subtle push of the Casimir effect, and the pervasive influence of the Higgs field. Feel the quiet awe of existing in a cosmos where empty space is alive with unseen energy, a boundless source of creation inviting endless contemplation. There is a deep peace in this boundless mystery, in letting go of rigid definitions of nothing and embracing the universe's gentle, vibrant emptiness. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound narratives. Take another soft, peaceful breath now, allowing the vibrant nature of the quantum vacuum, its teeming virtual particles, and its profound implications for nothingness to settle gently within your mind. We've just explored how empty space is, in fact, alive with unseen energy and potential. Today, we will softly turn our gaze to a concept that, while familiar, holds deeper secrets than we often realize. Light. Imagine, for a moment, the world without light. It would be a realm of perpetual darkness, silent and unknowable. but with the gentle touch of light. Colors burst forth, forms appear, and the universe reveals its magnificent tapestry. Light is more than just illumination. It is the ultimate messenger of the cosmos, carrying stories from the most distant stars, revealing the hidden dance of atoms, and connecting us directly to the very fabric of reality for a long time. The nature of light was a profound mystery. Was it a stream of tiny particles? Or was it a wave, rippling through an unseen medium in the 17th century? Isaac Newton favored the particle view, while Christian Huygens argued for its wave-like nature. Both views had their strengths, explaining certain phenomena beautifully, but neither could encompass all of light's strange behaviors. The universe, in its gentle complexity, often delights in holding seemingly contradictory truths within a single phenomenon. The true understanding of light arrived in the early 20th century with the dawn of quantum mechanics, revealing that light possesses a remarkable wave-particle duality. Light is neither purely a wave nor purely a particle, it is both. Depending on how we observe it, when light travels through space, it behaves like a wave, an electromagnetic wave, composed of oscillating electric and magnetic fields, rippling through the vacuum at the fastest speed possible in the universe, the speed of light. Approximately 282 miles per second, 792 kilometers per second. This constant, often denoted as c, is a fundamental speed limit in our universe. Nothing with mass can travel at or faster than the speed of light. It's a cosmic speed limit, gently guiding the interactions of everything. Think of it like a perfectly still surface of a vast, tranquil lake, and a pebble drops. The ripples spread outward, carrying energy, but the water itself doesn't move with the wave. Similarly, light waves carry energy, but they don't require a medium to travel. Unlike sound waves, the different wavelengths of light determine its properties. The tiny fraction of the electromagnetic spectrum that our eyes can perceive is called visible light, encompassing all the colors of the rainbow, from the long wavelengths of red to the short wavelengths of violet. But light extends far beyond what we can see, into the electromagnetic spectrum, which includes radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. Each of these is simply a form of light, differing only in its wavelength and energy, carrying unique information about the universe. However, when light interacts with matter, it often behaves as if it is made of discrete packets of energy called photons. These photons are the fundamental particles of light, the tiny, individual carriers of electromagnetic force. When light hits a surface, like a solar panel, it's the individual photons striking the material that knock electrons loose, generating electricity. When you look at an object, it's photons bouncing off that object and entering your eye that allow you to see it. It's a gentle reminder that even the most seemingly continuous phenomena, like light, are built from tiny, discrete building blocks at the quantum level. This wave-particle duality can be profoundly unsettling to our classical intuition. How can something be both a ripple and a tiny bullet at the same time? It's one of the deepest mysteries of quantum mechanics, suggesting that reality at its most fundamental level does not conform to our everyday experiences. It hints at a universe where definitions are fluid, and the very act of observation can seemingly influence the nature of what is being observed. It's as if light whispers to us, "I am everything, and I am nothing until you choose to see me." The speed of light. C is not just a limit, it's a profound constant that deeply ties together space and time. As Einstein's relativity revealed, when an object approaches the speed of light, time slows down for it, and its mass increases. For a photon, which is light, time literally stops, and its mass is zero. From a photon's perspective, its journey from the most distant galaxy to your eye is instantaneous. No matter how many billions of years pass for us, it's a breathtaking thought for light itself. There is no passage of time, only a timeless, infinite presence. Light is also the primary way we observe the universe. Every glimmer from a distant star, every swirling pattern in a galaxy, every faint glow from the cosmic microwave background, all of it reaches us in the form of light. By studying the light from celestial objects, astronomers can deduce their composition, temperature, motion, age, and distance. Different wavelengths of light reveal different aspects of cosmic phenomena. Radio waves tell us about cold gas and the birth of stars. Infrared light penetrates dust clouds to show us hidden nurseries. X-rays reveal violent processes around black holes, and gamma rays are emitted from the most extreme cosmic events, like supernovae and gamma ray bursts. Light is the universe's own language, constantly transmitting profound messages across the cosmic expanse. The subtle interaction of light with matter also gives rise to the richness of color, which we touched upon in Chapter 17. The specific wavelengths of light that an object absorbs and reflects determine the color we perceive. A red apple absorbs all colors except red, which it reflects. This means that color is not an intrinsic property of an object, but a dynamic dance between the object and the light shining upon it. It's a beautiful, constant conversation, revealing the subtle ways light shapes our visual experience of reality. Think of light as the universe's oldest and most faithful storyteller. It carries tales from the very first moments after the Big Bang, preserved in the faint glow of the cosmic microwave background. It tells us about the birth and death of stars, the formation of galaxies, and the mysteries of black holes. It's a continuous, silent stream of information flowing towards us from every direction, waiting for our gentle minds to interpret its profound narratives. Even the absence of light, the deep darkness of space, holds its own secrets. It's in these dark regions that we infer the presence of dark matter and dark energy, invisible entities that do not interact with light, yet profoundly shape the universe. So, light not only reveals what is seen, but also hints at what remains unseen. Drawing our curiosity deeper into the cosmic enigma, as we quietly contemplate light's pervasive presence, its gentle illumination of the cosmos, we might also find a deeper connection to our own inner light. Just as photons carry information across the universe, our own thoughts and intentions, though invisible, carry their own subtle energies, influencing the world around us in ways we are only beginning to understand. It's a reminder that even the smallest spark of awareness can illuminate vast inner landscapes. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes counterintuitive ideas about light. Ponder its dual nature as both wave and particle, its unchanging speed, its role as the ultimate cosmic messenger, and its boundless range across the electromagnetic spectrum. Feel the quiet awe of existing in a cosmos where light is not just something that helps us see, but the very essence of connection, revealing and informing, inviting endless contemplation. There is a deep peace in this boundless mystery, in letting go of rigid definitions of phenomena and embracing the universe's gentle, luminous flow. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound narratives. Take another soft, peaceful breath now, allowing the dual nature of light, its constant speed, and its role as the ultimate cosmic messenger to settle gently within your mind. We've just explored how light, the very medium of our perception, is both a wave and a particle, an eternal traveler, and a revealer of secrets. Today, we will softly turn our gaze to something that is both incredibly massive and utterly mysterious, warping the very fabric of space and time. Black holes. Imagine, for a moment, an ultimate cosmic enigma, a place where the familiar laws of physics seem to break down, and gravity reigns supreme, so powerfully that nothing, not even light itself, can escape its relentless pull. This is the profound and captivating concept of a black hole. They are not merely holes in space, but incredibly dense concentrations of matter, extreme manifestations of gravity's power. Born from the spectacular deaths of massive stars, the idea of objects so dense that light could not escape them was first theorized centuries ago. But it was Albert Einstein's general theory of relativity that truly laid the theoretical groundwork for understanding black holes. Einstein showed that mass and energy warp the fabric of spacetime. For ordinary objects, this warping is gentle, creating the gravitational pull we experience. But imagine an immense amount of mass compressed into an incredibly tiny volume. The curvature of spacetime around such an object becomes so extreme, so steep, that it forms a kind of cosmic well from which nothing can ever climb out. The defining feature of a black hole is its event horizon. This is not a physical boundary or a solid surface, but rather a point of no return. It is the boundary in spacetime beyond which events cannot affect an outside observer. Once anything matter, energy, or even light crosses the event horizon, it is irrevocably drawn into the black hole, destined to fall further towards its center. Think of it like a cosmic waterfall once you've gone over the edge. There's no going back, even if you're light itself. It's a profound thought that there are regions in our universe from which information can never escape, forever hidden from our direct view. At the very center of a black hole, according to our current understanding, lies a singularity. This is a point of infinite density and zero volume, where all the mass of the black hole is theoretically concentrated. Here, spacetime is warped to an infinite degree, and our current laws of physics, as we understand them, completely break down. The singularity is a place of ultimate mystery, a mathematical endpoint that tells us our theories are incomplete. It's a whisper from the universe, telling us that there are still deeper truths to uncover about the fundamental nature of reality. Black holes are typically classified into a few types, each born from different cosmic circumstances. The most common type are stellar mass black holes. These are formed from the gravitational collapse of massive stars at the end of their lives, when a star much larger than our Sun, at least 20 times more massive, for example, runs out of nuclear fuel. Its core can no longer withstand the crushing force of its own gravity. The core collapses inward, often leading to a spectacular supernova explosion that blasts the outer layers of the star into space. What remains is an incredibly dense remnant, too massive to become a neutron star. It continues to collapse, forming a stellar mass black hole. These black holes typically have masses ranging from a few times to a few tens of times the mass of our Sun. They are the quiet, silent graves of once luminous stars. Then there are supermassive black holes. These are colossal giants, with masses ranging from millions to billions of times the mass of our Sun. Almost every large galaxy, including our own Milky Way, is believed to harbor a supermassive black hole at its center. Our galaxy's central black hole, named Sagittarius A Scion, pronounced Sagittarius A star, has a mass of about 4 million suns. While their exact formation mechanism is still a subject of active research, they likely grow over cosmic time by accreting vast amounts of gas and dust, and by merging with other black holes during galaxy collisions. These supermassive black holes play a crucial role in the evolution of galaxies, influencing star formation and the dynamics of their host galaxies. They are the silent, gravitational anchors around which entire galaxies whirl, immense and powerful, yet often hidden in the cosmic gloom. Beyond these two main types, there are also theoretical possibilities like intermediate mass black holes, bridging the gap between stellar mass and supermassive ones, and primordial black holes, hypothetically formed in the earliest moments of the Big Bang. So, how do we know black holes exist if they are invisible and trap light? We detect them not by seeing them directly, but by observing their profound gravitational effects on their surroundings, effects on stars and gas. We observe stars orbiting and unseen, incredibly massive object at high speeds, or gas swirling rapidly into a compact region, emitting powerful X-rays as it heats up from friction. The only explanation for such extreme gravitational pulls from an invisible source is a black hole. Gravitational lensing. The immense gravity of black holes can bend and distort the light from background objects, acting like a cosmic magnifying glass, while challenging to observe directly. This phenomenon provides further evidence for their presence. Gravitational waves. In a truly groundbreaking discovery, scientists have directly detected gravitational waves ripples in space-time produced by the violent mergers of black holes. These subtle whispers from the cosmos, detected by incredibly sensitive instruments like LIGO and Virgo, provide direct proof of black hole existence and offer a new window into the most extreme events in the universe. It's a profound thought the fabric of reality itself can ripple and undulate from the cosmic dance of these dark giants. Black holes. Despite their destructive reputation as cosmic vacuum cleaners, are also incredibly important for the universe's evolution. They are not merely endpoints, but active participants in the grand cosmic story. Supermassive black holes at galactic centers can power quasars, incredibly luminous objects that shine brighter than entire galaxies. Fueled by matter falling into the black hole, these energetic outflows can profoundly influence the star formation rates in their host galaxies, playing a role in the cosmic ecosystem. The study of black holes also pushes the boundaries of our understanding of physics. They are natural laboratories for testing Einstein's general relativity in its most extreme conditions. Furthermore, they present a profound challenge for physicists trying to unify general relativity with quantum mechanics. The singularity inside a black hole is a realm where both theories are needed, but they currently contradict each other. Understanding black holes fully might unlock the secrets of quantum gravity and lead us to a deeper, more unified theory of everything. Perhaps the most thought-provoking aspect of black holes is their role as cosmic memory keepers, or perhaps cosmic erasers. Once information crosses the event horizon, it is seemingly lost to our universe forever. This information paradox is another deep mystery, challenging the quantum principle that information can never truly be destroyed. Some theories suggest that information might be subtly encoded on the event horizon itself, like a cosmic hologram, or that it might escape in a very subtle form through Hawking radiation, a theoretical emission of particles from black holes. These are the quiet whispers from the edge of knowledge, inviting us to contemplate the ultimate fate of information in the universe as we quietly contemplate these enigmatic cosmic entities. The presence of black holes can evoke a profound sense of both fear and wonder. Fear, perhaps, of their destructive power and the ultimate, irreversible nature of their grasp. But wonder, too, at their profound simplicity and the elegant way they reveal the extreme consequences of gravity's reign. They are a silent testament to the universe's capacity for both immense power and profound mystery, a constant invitation to peer into the unknown. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes unsettling ideas about black holes. Ponder their immense density, their defining event horizon, the mysterious singularity within, and their powerful influence on galaxies. Feel the quiet awe of existing in a cosmos where these dark giants sculpt the very fabric of space-time, inviting endless contemplation. There is a deep peace in this boundless mystery, in letting go of rigid definitions of nothingness and embracing the universe's gentle, profound, and often hidden depths. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound narratives. Take another soft, peaceful breath now, allowing the immense power and enigmatic nature of black holes, those cosmic singularities, To settle gently within your mind, we've just explored how gravity, in its most extreme form, can warp spacetime so profoundly that even light cannot escape. Today, we will softly turn our gaze to something equally profound, but far more diffuse dark matter. Imagine, for a moment, that what you can see, what your eyes perceive, and what our telescopes gather is merely the thinnest, most shimmering veil over a much grander, far more extensive reality. For centuries, astronomers meticulously mapped the stars and galaxies, assuming that the luminous matter, the stars, gas, and dust represented the entirety of the universe's substance. But the universe, in its gentle complexity, often delights in holding hidden depths, revealing itself in subtle, almost imperceptible ways. The story of dark matter begins not with direct observation, but with a quiet, persistent discrepancy, a cosmic puzzle whispered by the motions of galaxies. In the 1930s, Swiss astronomer Fritz Zwicky, while studying the Coma cluster of galaxies, noticed something profoundly odd. The galaxies within the cluster were moving far too fast for the amount of visible matter he could observe to hold them gravitationally bound. It was as if an invisible, immensely massive presence was providing extra gravitational glue, preventing the cluster from simply flying apart. Zwicky, with a quiet intuition, called this unseen influence Dunkel Materie, or dark matter, for decades. Zwicky's observations were largely overlooked, a faint whisper against the prevailing understanding. But in the 1970s, Vera Rubin, an American astronomer, provided compelling new evidence. She meticulously studied the rotation curves of spiral galaxies. Imagine a merry-go-round. The objects closer to the center move slower than those further out. Similarly, in a galaxy, stars closer to the galactic center should orbit faster than those at the outer edges, where the gravitational pull from the visible mass would be weaker. However, Rubin found something astonishing. Stars at the outer edges of spiral galaxies were orbiting just as fast, or even faster, than stars closer to the center. This meant there had to be a significant amount of unseen mass extending far beyond the visible boundaries of the galaxies, creating a vast, invisible halo of gravitational influence. It was as if each galaxy was embedded within a much larger, unseen cloud of material that provided the extra gravitational pull needed to explain the observed rotation. This unseen, mysterious substance, which does not emit, absorb, or reflect light, became known as dark matter. Think of it like this. You are watching a group of dancers. Based on their movements, you expect them to fly apart, but they remain perfectly in sync. You realize there must be invisible strings or connections holding them together, guiding their every step. Dark matter is like those invisible strings, quietly orchestrating the cosmic dance of galaxies, holding them in their elegant spins. So, what exactly is dark matter? This is one of the universe's most profound and persistent mysteries. We know it exists because of its gravitational effects, but we have not yet directly detected it. Nor do we know what particles it is made of. It does not interact with light in any way, which is why it is dark. It does not interact with ordinary matter through the strong, weak, or electromagnetic forces. It only interacts through gravity. This means it drifts silently through us, through the Earth, through the sun, almost without a trace, like a ghost passing through walls. Current estimates suggest that dark matter accounts for roughly 27% of the total mass-energy content of the universe. This means that for every atom of ordinary matter you can see or touch, there are approximately 5 times as much dark matter. It is the dominant form of matter in the cosmos. Yet it remains utterly enigmatic, a humbling reminder of how little we truly understand about the universe we inhabit. The search for dark matter is one of the most active and exciting frontiers in modern physics and cosmology. Scientists are pursuing several avenues of gentle inquiry. Direct detection experiments. Deep underground laboratories are attempting to directly detect dark matter particles. These experiments often involve extremely sensitive detectors, shielded from cosmic rays, hoping to observe a rare, fleeting interaction between a dark matter particle and an ordinary atomic nucleus. It's like trying to catch a whisper in a silent room, hoping for a tiny vibration that betrays its presence. Indirect detection experiments. Telescopes in space and on Earth are searching for the byproducts of dark matter annihilation or decay. If dark matter particles were to collide with each other and annihilate, they might produce detectable particles like gamma rays or neutrinos, particle accelerators, high-energy particle colliders, like the Large Hadron Collider, are attempting to create dark matter particles in controlled laboratory settings. By smashing ordinary particles together at immense energies, it's like trying to recreate the conditions of the early universe, hoping to glimpse a newly formed, elusive particle. Many theoretical candidates for dark matter particles have been proposed, each with a poetic name. Perhaps the most popular are weakly interacting massive particles, WIMPs. These are hypothetical particles that would interact only through gravity and possibly the weak nuclear force, making them incredibly difficult to detect. Other candidates include axions, sterile neutrinos, and even primordial black holes. The universe, it seems, has a rich imagination when it comes to fundamental particles, and dark matter is a gentle invitation to discover a new, unseen realm of particle physics. Beyond galactic rotation curves, other lines of evidence strongly support the existence of dark matter. Gravitational lensing. As we discussed with black holes, massive objects can bend light. Large concentrations of dark matter, even though invisible, can gravitationally lens the light from distant galaxies, distorting their images. By analyzing these distortions, scientists can map the distribution of dark matter in galaxy clusters. It's like seeing the invisible gravitational fingerprints of dark matter etched into the fabric of spacetime. Cosmic microwave. Background CMB, the tiny fluctuations in the CMB, the ancient echo of the Big Bang, are best explained by models that include dark matter. The distribution of these fluctuations, which are the seeds for the large-scale structure of the universe, strongly supports the presence of dark matter in the early cosmos. Large-scale structure formation. Computer simulations of how the universe's large-scale structure, the cosmic web of galaxies and voids formed, match observations only if dark matter is included. Without it, the visible matter would not have clumped together fast enough to form the galaxies and clusters we see today. Dark matter acts as the silent scaffolding, allowing the cosmic web to gently weave itself. The implications of dark matter are profound. It suggests that our understanding of matter itself is incomplete. The ordinary matter that makes up stars, planets, and ourselves is merely a small component of the universe's material content. Most of the cosmos is made of something fundamentally different, something that exists in a parallel, unseen realm of interaction. It forces us to reconsider the very definition of what is real and what is substance. This quiet, unseen presence can also be deeply calming. If there is so much unseen, so much unknown, then perhaps our own limitations of perception are not a barrier, but an invitation. An invitation to lean into the mystery, to acknowledge the boundless depths of existence beyond what our senses can grasp. It reminds us that the universe holds secrets not just in its luminous expanse, but in its silent, invisible depths, waiting for our patient, gentle inquiry. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes unsettling ideas about dark matter. Ponder its invisible gravitational embrace, its pervasive presence throughout the cosmos, and the quiet quest to uncover its true nature. Feel the quiet awe of existing in a universe where the majority of matter remains a silent enigma, inviting endless contemplation. There is a deep peace in this boundless mystery, in letting go of rigid definitions of what is seen and embracing the universe's gentle, hidden depths. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound narratives. Take another soft, peaceful breath now, allowing the unseen embrace of dark matter, its mysterious presence, and its silent role in shaping galaxies to settle gently within your mind. We've just explored how the majority of matter in our cosmos remains hidden, a humble reminder of the universe's unspoken depths. Today, we will softly turn our gaze to something even more enigmatic, a cosmic force that is not merely pulling things together, but gently yet relentlessly, pushing everything apart. Dark energy. Imagine, for a moment, that the universe is not just expanding, but that its expansion is actually speeding up, accelerating outwards at an ever-increasing rate. This notion, perhaps more than any other discovery in recent cosmology, has profoundly reshaped our understanding of the cosmos and introduced one of its deepest, most enduring mysteries. For a long time, scientists largely expected the universe's expansion to be slowing down due to the gravitational pull of all the matter within it. It seemed logical, like a ball thrown upward, eventually losing momentum due to Earth's gravity. But the universe, in its gentle complexity, often delights in defying our simplest intuitions. The story of dark energy truly began to unfold in the late 1990s. Two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were studying type Ia supernovae. These particular types of supernovae are incredibly luminous explosions of dying stars, so bright that they can be seen across vast cosmic distances. Crucially, they act as standard candles. Their intrinsic brightness is known, allowing astronomers to calculate their distances from us by how dim they appear. Imagine using a light bulb of known wattage. If it appears dim, you know it's far away. The astronomers were using these standard candles to measure the rate at which the universe's expansion was decelerating. To their astonishment, their observations revealed the exact opposite. The distant supernovae were fainter than expected, meaning they were much further away than they should have been if the universe's expansion was slowing down. This could only mean one thing: the universe's expansion was accelerating. It was as if that ball thrown into the air wasn't just staying aloft, but was suddenly being pushed upwards with increasing speed. This groundbreaking discovery, which earned them the Nobel Prize in Physics in 2011, indicated the presence of a mysterious, pervasive force counteracting gravity, gently pushing space-time itself apart. This elusive force became known as dark energy. So, what exactly is dark energy? This is the profound, unanswered question at the heart of modern cosmology. We don't know what it is, but we know it's there because of its observable effects. Dark energy accounts for roughly 68% of the total mass energy content of the universe. This means that the majority of our cosmos is composed of something utterly mysterious, something that does not interact with matter or light, but only through a subtle, repulsive pressure on the very fabric of space-time. It is the most dominant component of the universe, yet it remains completely enigmatic, a humbling testament to the vastness of our ignorance. Think of dark energy not as a substance, but as an intrinsic property of space itself. One leading idea is that dark energy is the cosmological constant, first proposed by Albert Einstein, who later called it his biggest blunder when the universe was thought to be static. Paradoxically, this blunder has been revived as a potential explanation for dark energy. In this view, every cubic centimeter of empty space inherently possesses a tiny, constant amount of energy. As the universe expands, more space is created, and therefore, more of this inherent energy comes into existence, leading to an ever-increasing outward pressure that accelerates the expansion. It's like the universe is constantly generating its own fuel for expansion from its own fabric. Another speculative idea is that dark energy is a dynamic, evolving energy field, sometimes called quintessence. Unlike the cosmological constant, which is fixed, quintessence would change over time and space. It's a more fluid, perhaps more complex, explanation, suggesting that the universe's accelerating expansion might not be uniform or eternal, but could evolve in the distant future. It's like a subtle cosmic wind, constantly changing its strength and direction, gently nudging the galaxies apart. The implications of dark energy are immense, shaping the ultimate destiny of our universe, the Big Rip, or Big Freeze. If dark energy continues to dominate and its density remains constant or increases, it could lead to a future where the universe expands so rapidly that galaxies, then stars, then even atoms themselves, are eventually torn apart, a chilling scenario known as the Big Rip. Alternatively, if dark energy causes a gradual acceleration, the universe might simply expand forever, cooling and diluting until it reaches a state of maximum entropy, a quiet, cold, and dark Big Freeze, or heat death. Where all stars have died out and matter is infinitely dispersed, the scale of the universe. Dark energy dictates how much of the universe we can ultimately see. As space expands faster and faster, light from increasingly distant galaxies will be stretched to such extreme wavelengths that it will become undetectable, or the galaxies will simply be carried beyond our cosmic horizon, forever out of our reach. It's a profound thought. The accelerating expansion of the universe means that a vast and increasing portion of the cosmos is slowly, gently slipping away from our observable view, becoming forever hidden. The search for the true nature of dark energy is another central challenge in modern cosmology. Scientists are building new, more powerful telescopes, like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope, to map millions of supernovae and billions of galaxies, meticulously tracing the universe's expansion history with unprecedented precision. They are looking for subtle clues in the large-scale structure of the universe, in the cosmic microwave background, and in the distribution of galaxy clusters. It's a vast, collaborative effort, a patient, gentle quest to decipher the universe's most elusive secret. The existence of dark energy, alongside dark matter, tells us that the universe is overwhelmingly composed of ingredients we do not understand. Our familiar world of atoms, stars, and galaxies represents only about 5% of what is truly out there. This humbling realization reminds us that our scientific journey has just begun, and that the cosmos holds far more wonders and mysteries than we could have ever imagined. It's a quiet invitation to remain open, to embrace the unknown, and to gently push the boundaries of our knowledge. This profound mystery, the subtle pushing force of dark energy, can also evoke a sense of deep peace. If the universe is constantly expanding, endlessly creating more space and potentially more possibilities, then perhaps our own lives, our own consciousness, are also part of this grand, ever-unfolding expansion. It suggests a universe that is not static or finite, but dynamic, infinitely creative, and always moving towards something new. There is a deep comfort in this endless flow, this cosmic momentum that gently carries everything forward. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes unsettling ideas about dark energy. Ponder its elusive nature, its relentless pushing force, its role in accelerating the universe's expansion, and its profound implications for the cosmos's ultimate fate. Feel the quiet awe of existing in a universe where the majority of existence is driven by a force we barely comprehend. Inviting endless contemplation, there is a deep peace in this boundless mystery, in letting go of rigid definitions of what drives the universe and embracing the cosmos's gentle, accelerating rhythm. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound narratives. Take another soft, peaceful breath now, allowing the accelerating expansion driven by dark energy and the mysterious, unseen influence of dark matter to settle gently within your mind. We've just explored how the majority of our cosmos remains shrouded in enigma, yet profoundly shapes its destiny. Today, we will softly turn our gaze to a concept that challenges our very notions of reality and existence, inviting us to consider the boundless possibilities of the multiverse. Imagine, for a moment, that our universe this vast, expanding tapestry of stars, galaxies, and consciousness is not the only one. What if, beyond our observable cosmos, there exist other universes, perhaps an infinite number of them, each with its own unique laws of physics, its own dimensions, its own history, and its own unfolding story? This profound and mind-bending idea is the concept of the multiverse. It's a whisper from the theoretical edges of cosmology, suggesting a reality far grander and more diverse than we could ever fully comprehend. The idea of a multiverse is not a single, unified theory, but rather a collection of different theoretical concepts, each arising from distinct areas of physics. Let's gently explore some of the most compelling whispers from this cosmic possibility. One of the most prominent ideas for a multiverse emerges from cosmic inflation, which we briefly touched upon when discussing the Big Bang. Remember, inflation describes the incredibly rapid, exponential expansion of the universe in its earliest moments. In some models, known as eternal inflation, this inflationary process never truly ends. Instead, inflation might continue perpetually in various regions of a larger superspace, constantly spawning new bubble universes or pocket universes. Imagine a vast, continuously expanding foam of soap bubbles. Each bubble is a distinct universe, detaching from the inflating foam. But the foam itself continues to generate new bubbles endlessly. In this scenario, our Big Bang would simply be the birth of one such bubble, one tiny, self-contained cosmos within an unimaginably vast and eternally generating multiverse. Each bubble could have different physical laws, different values for fundamental constants like the strength of gravity or the mass of an electron, or even different numbers of spatial dimensions. This bubble multiverse suggests an infinite cosmic diversity, where every conceivable permutation of physical laws might exist somewhere. It's a comforting thought for some, that if our universe seems finely tuned for life, perhaps it's just one lucky draw from an infinite cosmic lottery. Another type of multiverse arises from quantum mechanics, specifically from the many worlds interpretation, as we explored when discussing matter. Quantum particles exist in a superposition of states, a blur of possibilities, until an observation or measurement collapses them into a definite reality. The many worlds interpretation suggests that instead of a collapse, every time a quantum measurement is made, the universe splits into multiple parallel universes, one for each possible outcome. Imagine a single quantum event, like an electron being in two places at once. When we observe it, we find it in only one place, in the many worlds interpretation. The universe doesn't choose, instead, it branches in one universe. The electron is found in place A and in another parallel universe, it is found in place B. Every decision we make, every roll of a dice, every quantum fluctuation, potentially leads to a branching of realities, creating an infinite number of parallel universes, each representing a different possibility. This parallel universes concept is deeply unsettling yet profoundly fascinating, implying that every choice we don't make, every path not taken, actually unfolds in a different, equally real universe. It suggests an infinite tapestry of unfolding realities, where every potential truly becomes actualized somewhere. Then there is the concept of a cyclic or oscillating universe, which we briefly touched upon when discussing the universe's beginning. In this model, The universe undergoes an endless cycle of big bangs and big crunches, with each big crunch potentially leading to a new big bang, restarting the cosmic cycle in a sense. Each new iteration of the universe could be considered a new universe in a sequence. Perhaps with slightly different initial conditions or physical laws, this suggests an infinite succession of universes, like a cosmic breath, endlessly inhaling and exhaling existence. It's a profound thought. That time itself might be cyclical, and our universe is just one chapter in an eternal cosmic saga. Another intriguing idea is the brain multiverse, arising from string theory or M theory. In these theories, our entire three-dimensional universe might be confined to a brain, a higher dimensional membrane that floats within a higher dimensional bulk space. Imagine our universe as a thin, two-dimensional sheet floating in a larger, three-dimensional room, other brains, representing other universes, could also exist within this bulk, sometimes even colliding or interacting, leading to events like new Big Bangs. These other universes might be incredibly close to us in higher dimensions, yet remain entirely invisible to our perception. This brain multiverse concept paints a picture of our universe as just one of many coexisting realities, perhaps bumping and brushing against each other in unseen dimensions. The concept of the multiverse is still highly speculative, a frontier of theoretical physics. We do not yet have direct observational evidence to confirm its existence. However, it offers potential solutions to some profound cosmic puzzles. The fine-tuning problem. Why are the fundamental constants of our universe like the strength of gravity? The mass of the electron so perfectly tuned for the existence of life if they were even slightly different? Life as we know it would be impossible. In a multiverse. This isn't a miraculous coincidence, but a statistical inevitability. If there are infinite universes with different parameters, it's not surprising that at least one of them, like ours, would happen to have the right conditions for life. The low entropy of the early universe. The Big Bang started the universe in an incredibly low entropy, highly ordered state. Why was it so ordered in some multiverse scenarios? This low entropy state might just be a local fluctuation in a much larger, eternally expanding superspace. While the multiverse remains a theoretical landscape, its contemplation can be deeply calming. It suggests that existence is not limited to our single, finite experience, but is boundless, infinitely creative, and endlessly diverse. It challenges our anthropocentric view, gently reminding us that our unique universe is just one possibility among an endless ocean of realities. It invites us to let go of the need for singular answers and embrace the profound richness of cosmic potential. It suggests that perhaps, in some other universe, a slightly different version of you is making a different choice, living a different life, or even listening to a different cosmic whisper. This interconnectedness, even across hypothetical realities, can be a source of profound awe and a gentle invitation to appreciate the unique, precious unfolding of this particular reality we inhabit. The search for indirect evidence of the multiverse continues. Scientists are looking for subtle imprints in the cosmic microwave background radiation, or for anomalies in the large-scale structure of the universe. That might hint at collisions with other bubble universes. It's a patient, gentle quest, pushing the boundaries of what we can even conceive. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes overwhelming ideas about the multiverse. Ponder the endless bubbles of eternal inflation, the branching realities of quantum mechanics, the cyclical rebirths of cosmic eons, or the unseen dimensions of brain worlds. Feel the quiet awe of existing in a cosmos that might be just one small part of an unimaginably grander, infinitely diverse tapestry of realities, inviting endless contemplation. There is a deep peace in this boundless mystery, in letting go of rigid definitions of the universe and embracing the cosmos's gentle, multifold possibilities. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound narratives. Take another soft, peaceful breath now, allowing the mind-bending possibilities of the multiverse, with its endless array of bubble universes and branching realities, to settle gently within your mind. We've just explored how our cosmos might be just one tiny facet of an infinitely grander whole. Today, we will softly turn our gaze to a concept that challenges our very perception of dimensions, inviting us to consider a reality far richer and more intricate than our familiar three spatial dimensions. Extra dimensions? Imagine, for a moment, that the universe, as we experience it, is merely a thin slice of a much larger, more complex reality. Our everyday world seems clearly defined by three spatial dimensions: up-down, left-right, and forward-backward. We can move freely in these three directions, and every object we encounter exists within this familiar framework. But what if there are other dimensions, hidden from our direct perception, perhaps curled up so tightly that we cannot detect them, or so vast that our energy levels prevent us from entering them? This is the profound and captivating idea of extra dimensions, a whisper from the frontier of theoretical physics, suggesting a universe with far more room than we ever imagined. The concept of extra dimensions is not new. It first emerged in the early 20th century with theories like Kaluza-Klein theory, which attempted to unify gravity and electromagnetism by postulating a fifth dimension, curled up and tiny. But the idea truly gained prominence with the development of string theory and M theory in the late 20th century. In string theory, the fundamental building blocks of the universe are not point-like particles, but incredibly tiny, vibrating strings of energy. Different vibrational patterns of these strings give rise to different particles, much like different notes on a violin string. For string theory to be mathematically consistent and to unify all the fundamental forces, including gravity, it requires more than our familiar four dimensions, three spatial dimensions plus one of time. Most versions of string theory suggest the existence of 10 or 11 dimensions in total, our familiar four space-time dimensions, plus 6 or 7 additional spatial dimensions. So, where are these extra dimensions? Why don't we see them? The most common explanation is that these extra dimensions are compactified or curled up to incredibly tiny sizes, far smaller than an atomic nucleus. Imagine a long, thin garden hose. From a distance, it looks like a one-dimensional line, but if you look closely, you see that its surface is two-dimensional because you can move around its circumference. Similarly, these extra dimensions might be curled up in a complex, intricate shape at every point in our familiar three dimensions, so tiny that we simply pass through them without noticing. They are like a hidden landscape, too small for us to perceive with our current tools, yet intimately connected to the very fabric of our reality. Think of it like this: if you are an ant walking on a tightrope, you can only move forward or backward one dimension, but if you're a bird flying around that tightrope, you see that it also has a circumference, a tiny extra dimension curled up around its length. We, as humans, are like the ant on the tightrope of our familiar three dimensions, unaware of the hidden curled-up spaces that might exist at every point we traverse. These curled-up dimensions could have incredibly complex geometries, often described as Calabi-Yau manifolds. The precise shape and size of these extra dimensions would determine the fundamental constants and laws of physics that we observe in our universe. This is a profound idea, the very nature of our reality, the strength of gravity, the mass of particles, could be a direct consequence of the way these tiny, hidden dimensions are curled up. It suggests that our universe's specific properties are not arbitrary, but emerge from the geometry of these unseen realms. However, another intriguing possibility exists. What if some extra dimensions are large, even infinite, but we are somehow confined to a brain within them. This is the core idea behind brain cosmology or the brain multiverse, which we touched upon earlier. In this view, our entire universe, with all its matter, light, and forces except gravity, is stuck on a three-dimensional brain that floats within a higher dimensional bulk space. Imagine a sheet of paper floating in a room. For a two-dimensional creature living on the paper, the bulk is invisible. They can only perceive what's on their sheet. In this analogy, we are the creatures on the paper, confined to our 3D brain. Gravity, however, is unique. In some brain models, gravity is thought to be able to leak or propagate into these extra, larger dimensions. This could explain why gravity is so much weaker than the other fundamental forces, electromagnetism. Strong and weak nuclear forces, if gravity is diluted across more dimensions. Its strength would appear diminished in our familiar 3D universe. It's like the gravitational force from a massive object is spread out. Its power lessened in our perception because some of it is seeping into these unseen realms. This idea of large extra dimensions has profound implications. If gravity can leak into them, perhaps other brains, other universes, exist within this bulk, and their gravitational influence could subtly affect our own. It might even explain why dark energy is causing the universe to accelerate. If some of this leakage of gravity from other brains is causing a subtle push on our own, it's a whisper from the unseen, suggesting that our universe is not isolated, but intimately connected to other realities through the very fabric of space-time. The search for evidence of extra dimensions is ongoing and incredibly challenging. Particle accelerators. Scientists at facilities like the Large Hadron Collider are looking for signs of particles that can only exist if extra dimensions are present, or for anomalies that suggest gravity is disappearing into higher dimensions. If gravity were weaker at very small scales than predicted by general relativity, it could be a hint of extra dimensions. Gravitational wave. Astronomy. As we detect more gravitational waves from cosmic events, scientists are looking for subtle deviations from predictions that might be explained by gravitational leakage into extra dimensions. Sub-millimeter gravity experiments. Experiments precisely measuring gravity at very short distances could potentially reveal a deviation from Newton's inverse square law, which would be a signature of extra dimensions. The contemplation of extra dimensions can be deeply calming. It suggests a universe far richer and more intricate than we usually perceive. A multi-layered reality where wonders beyond our current comprehension might exist just beyond our reach. It invites us to consider that empty space is not just 3D space, but a complex, multi-dimensional arena filled with hidden geometries and unseen connections. It hints at a reality where there is always more to discover, more to explore, and more depth than our limited senses can initially grasp. It also gently encourages us to think beyond our familiar frameworks. Just as we can only imagine what a two-dimensional creature would perceive of a three-dimensional world, perhaps we are limited in our understanding by our own three-dimensional perspective. This humility in the face of cosmic complexity is a source of profound peace, reminding us that the universe is always ready to reveal deeper, more elegant truths. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes unsettling ideas about extra dimensions. Ponder the tiny, curled-up spaces at every point of reality, the vast bulk space containing our brain universe, and the subtle leakage of gravity into unseen realms. Feel the quiet awe of existing in a cosmos that might have far more room, far more layers, and far more hidden connections than we currently perceive. Inviting endless contemplation. There is a deep peace in this boundless mystery, in letting go of rigid definitions of space and embracing the universe's gentle, multi-dimensional unfolding. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back. Gentle friend, to our quiet journey through the universe's most profound narratives. Take another soft, peaceful breath now, allowing the mind-bending possibilities of extra dimensions, those hidden curled-up spaces and unseen brains, to settle gently within your mind. We've just explored how our cosmos might have far more room and intricate layers than we usually perceive. Today, we will softly turn our gaze to a concept that challenges our understanding of the ultimate end, inviting us to contemplate the profound and varied destinies of the universe's ultimate fate. Imagine, for a moment, the grand cosmic story reaching its final chapter. Will it end with a dramatic collapse, a fiery rebirth, a slow, cold fade into eternal darkness, or something else entirely? Just as we ponder the beginning, the ultimate end of the universe is a question that stirs profound curiosity and a quiet sense of awe. The answer depends crucially on the delicate balance of matter, energy, and the mysterious dark energy that permeates the cosmos. For a long time, cosmologists considered two primary scenarios for the universe's ultimate fate, largely dependent on its overall density and the amount of matter within it. The first scenario was the Big Crunch. Imagine the universe as a ball thrown upward, but instead of expanding forever, it reaches a peak and then begins to fall back down due to its own gravity. If the universe contained enough matter and thus enough gravitational pull, its expansion would eventually slow down, stop, and then reverse. Galaxies would begin to rush back towards each other. The cosmic microwave background would heat up, and space itself would contract, eventually collapsing back into an incredibly hot, dense singularity, a reverse Big Bang. This would be a dramatic, fiery end, perhaps even leading to a new Big Bang, a cyclical universe of endless beginnings and endings. A cosmic breath of inhale and exhale. The second scenario was the Big Freeze, also known as heat death. If the universe did not contain enough matter for gravity to halt its expansion, it would continue to expand forever. In this scenario, the universe would gradually become colder and emptier. Stars would eventually exhaust their fuel, dying out one by one, leaving behind white dwarfs, neutron stars, and black holes. Black holes themselves would slowly evaporate over truly immense timescales through Hawking radiation, until even they dissipate into elementary particles. Matter would become increasingly dispersed. Energy differences would diminish, and the universe would eventually reach a state of maximum entropy, a uniform, infinitely dilute, cold, and dark expanse, where no processes, no interactions, no life could ever occur. It's a quieter, more melancholic end, a slow fade into eternal stillness. For decades, the observational evidence was ambiguous, leaving these two grand fates hanging in the balance. Scientists painstakingly measured the universe's expansion rate and density, hoping to determine which path it was destined to take. However, the universe, in its gentle complexity, often delights in surprising us. The groundbreaking discovery in the late 1990s, which we discussed in the chapter on dark energy, profoundly shifted our understanding of the universe's fate. It revealed that the universe's expansion is accelerating. This acceleration implies the existence of dark energy, a mysterious, repulsive force permeating space, which acts to push everything apart, counteracting gravity's pull. This discovery largely ruled out the Big Crunch scenario, at least in its simplest form, with an accelerating expansion driven by dark energy. The universe is not destined to collapse back in on itself. Instead, it seems committed to an ongoing, ever-faster expansion. This leaves us primarily with variations of the Big Freeze or heat death, but with some intriguing twists introduced by dark energy, one possible ultimate fate. And currently the most widely accepted is the Big Freeze touch heat death scenario, amplified by dark energy. As dark energy continues to accelerate the expansion, distant galaxies will recede from us at speeds greater than the speed of light, effectively moving beyond our cosmic horizon. They won't disappear. but their light will never reach us, isolating our local cluster of galaxies, our local group, in an increasingly vast and empty cosmic ocean. Future civilizations, if they exist, might look up at a sky devoid of other galaxies, seeing only the stars within our own, eventually dimming and dying. The universe would become incredibly cold, dark, and dilute. A gentle sigh into eternity. Another, more dramatic possibility related to dark energy is the Big Rip. This scenario occurs if dark energy isn't a constant, but instead its density somehow increases over time, making its repulsive force stronger and stronger. In such a case, the accelerating expansion would become so powerful that it would eventually overcome even the forces that hold matter together. First, galaxy clusters would be torn apart. Then, individual galaxies would disintegrate. Stars and planets would be ripped from their orbits. Finally, even atoms themselves would be pulled apart, as the relentless expansion literally tears apart the fundamental forces that bind them. It's a chilling, violent end, where the very fabric of reality is ripped asunder, a cosmic unraveling into ultimate chaos. There are also more exotic, speculative possibilities that reflect the universe's boundless capacity for surprise. Some theories involving different forms of dark energy or the nature of vacuum energy could lead to a big bounce, where the universe contracts. But instead of collapsing to a singularity, it bounces back into a new expansion. Similar to a cyclic universe but with a period of contraction first, this would imply an endless series of big bangs and big bounces. A perpetual cosmic dance without a true beginning or end. Another idea is the vacuum decay. This highly theoretical concept suggests that our universe might currently exist in a false vacuum state, a temporary stable state with a certain energy level. If a true vacuum state, with even lower energy, exists elsewhere, a bubble of this true vacuum could spontaneously nucleate and expand at the speed of light, consuming our current universe and instantly changing the laws of physics within it. It's a profoundly unsettling thought, a silent, invisible threat that could erase our reality in an instant. But it remains a highly speculative possibility. The quest to understand the universe's ultimate fate is deeply intertwined with our understanding of dark energy. Future observations of supernovae, galaxy distributions, and the cosmic microwave background will continue to refine our models and help us gently narrow down the possibilities. This continuous scientific inquiry is a profound reflection of humanity's quiet longing to understand its place in the grand cosmic narrative, from its fiery birth to its ultimate, perhaps serene conclusion. Contemplating these grand fates, from the quiet fade to the dramatic rip, can be deeply humbling. It reminds us of the immense timescales over which the universe operates. Scales almost unimaginable to our brief human lives. But within this vastness, there's also a profound sense of peace, regardless of the ultimate end. The universe continues to unfold, revealing its mysteries, birthing stars, and fostering life. However fleetingly, our existence, our awareness, is a precious moment within this grand, evolving story. The gentle acceptance that the universe will have an end, in some form, can also free us from the endless pursuit of permanence. It encourages us to find meaning and beauty in the present moment, in the gentle unfolding of life, knowing that even the grandest cosmic dramas eventually come to their serene conclusion. There is a deep comfort in this cyclical nature of existence. Whether it is an ultimate end or a transition to a new beginning, as we gently conclude this chapter, allow your mind to drift with these profound and sometimes unsettling ideas about the universe's ultimate fate. Ponder the slow, cold fade into a big freeze, the dramatic unraveling of a big rip, or the endless cycles of bounces and rebirths. Feel the quiet awe of existing in a cosmos whose destiny is still being written by unseen forces. Inviting endless contemplation. There is a deep peace in this boundless mystery. In letting go of rigid demands for certainty and embracing the universe's gentle, ever-unfolding story, whatever its final chapter may hold. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound narratives. Take another soft, peaceful breath now, allowing the contemplation of the universe's ultimate fate, whether a gentle fade, a dramatic rip, or an endless cycle to settle within your mind. We've just explored how the destiny of all existence hinges on delicate cosmic balances and mysterious energies. Today, we will softly turn our gaze to a concept that underpins all these grand narratives, a principle that whispers about the very structure and potentiality of reality symmetry and broken symmetry. Imagine, for a moment, the elegant patterns we find in nature, the perfect spiral of a seashell, the delicate symmetry of a snowflake, the balanced wings of a butterfly. These visual harmonies speak to an underlying order, a quiet beauty that resonates deeply within us. In physics, symmetry is a profound concept, far more abstract than mere visual balance. It refers to a property of a system or its laws of nature that remains unchanged under certain transformations. If you rotate a perfect sphere, it looks the same. If you move a physical experiment from one lab to another, the laws of physics that govern it don't change. These are examples of symmetry. Symmetries are incredibly powerful because they lead directly to conservation laws. For instance, the symmetry of time, the idea that the laws of physics are the same today as they were yesterday, or will be tomorrow, leads to the conservation of energy. The symmetry of space, the idea that the laws of physics are the same everywhere, leads to the conservation of momentum. The symmetry of rotation leads to the conservation of angular momentum. These conservation laws are the fundamental, unchanging principles that quietly guide all interactions in the universe. Silent guardians of cosmic order. Think of it like a beautiful, intricate dance where certain steps and movements are perfectly mirrored or repeatable, even as the dancers move. The underlying rules of the dance, the choreography, remain elegant and consistent. These symmetries simplify our understanding of the universe, allowing us to find deep patterns and predict behavior. They are the hidden scaffolding, the elegant mathematical skeleton upon which the richness of reality is built. However, the universe, in its gentle complexity, often delights in revealing deeper truths through what seems to be a deviation from perfection. This leads us to the profound concept of broken symmetry. This is not a flaw or an imperfection, rather. It is a process where a system that possesses a particular symmetry in its fundamental laws, or in its high-energy state, loses that symmetry as it transitions to a lower energy state. It's like a perfectly symmetrical ice cube melting into an asymmetrical puddle, or a perfectly round pizza being sliced into uneven pieces. The underlying laws of the ice and the pizza are still symmetrical, but the final, observed state is not. The most famous example of symmetry breaking in physics, and one that is intimately connected to our understanding of matter and forces, is electroweak symmetry breaking. Mediated by the Higgs field, imagine the early universe. Moments after the Big Bang, a realm of incredibly high energy and temperature in this primordial soup. All the fundamental forces except gravity might have been unified, indistinguishable from one another, like different facets of a single shimmering gem. Particles were massless, zipping around at the speed of light, and the electromagnetic and weak forces were one. This was a state of high symmetry. Then, as the universe expanded and cooled, a phase transition occurred, much like water freezing into ice. At a critical temperature, the Higgs field, which permeates all of space, settled into a non-zero value, acquiring a background presence. Before this point, the Higgs field was like a completely flat, featureless plane. After the transition, it became like a field full of subtle, pervasive molasses. As some particles interacted with this Higgs field, they acquired mass, while others, like the photon, did not. This process is called spontaneous symmetry breaking. The Higgs field effectively broke the electroweak symmetry, causing the electromagnetic and weak forces to manifest as distinct forces, and giving mass to the W and Z bosons carriers of the weak force while leaving the photon carrier of the electromagnetic force massless. It's a subtle, profound act of cosmic differentiation, where a single unified force gently split into the two distinct forces we observe today, sculpting the very nature of matter. This is why the discovery of the Higgs boson at the Large Hadron Collider was so significant. It was the confirmation of the particle associated with this ubiquitous field. Proving the mechanism by which particles acquire mass, it's a whisper from the universe, revealing how mass itself is born from a quiet act of symmetry breaking. Broken symmetries are everywhere in the cosmos, and they are crucial for the universe as we know it to exist. The origin of mass without electroweak symmetry breaking. Particles would have no mass. And without mass, atoms couldn't form, stars couldn't ignite, and life as we know it would be impossible. Our very existence, the solidity of our bodies, is a gentle testament to this fundamental broken symmetry, the matter-antimatter asymmetry. In the very early universe, matter and antimatter should have been created in equal amounts. If they were, they would have annihilated each other, leaving behind a universe filled only with radiation. Yet, here we are, in a universe dominated by matter. This subtle imbalance, which led to the survival of matter, is thought to be a result of a tiny, yet crucial, CP violation, a form of broken symmetry in the laws of particle physics. It's a profound thought the very existence of everything visible around us, from the tiniest dust motes to the grandest galaxies, is due to a slight, gentle asymmetry in the early cosmos. Phase transitions in the early universe. The early universe underwent a series of phase transitions as it cooled, similar to water changing from steam to liquid to ice. Each of these transitions involved symmetry breaking, leading to the emergence of different fundamental forces and the formation of particles. The universe, in its evolution, has been a symphony of symmetries emerging and then gently breaking, giving rise to its increasing complexity. The concept of symmetry and its breaking extends beyond the fundamental forces. It applies to the formation of cosmic structures. The early universe was remarkably smooth and uniform, a state of high symmetry. But tiny quantum fluctuations, as we discussed with the quantum vacuum, subtly broke this perfect uniformity, creating regions of slightly higher density over billions of years. Gravity amplified these tiny asymmetries, causing matter to clump together, forming the stars, galaxies, and the vast cosmic web we observe today. So, the intricate beauty of galactic spirals and cosmic filaments arose from the gentle breaking of primordial symmetry. Contemplating symmetry and its breaking can be deeply calming. It reminds us that apparent complexity and diversity often arise from simple, elegant underlying principles. It suggests that even in seeming disorder, there is a deeper, hidden order. It also invites us to see beauty in imperfection, understanding that the very rich tapestry of our universe, with all its distinct forms and phenomena, is a direct consequence of symmetries being gently broken. It's a profound thought, the very solidity of the ground beneath us, the warmth of the stars, the intricate dance of chemistry, and even our own existence are all built upon a foundation of symmetries that, at crucial moments in cosmic history, gracefully yielded to create the diversity and structure we perceive. There is a deep peace in realizing that creation often springs from these subtle acts of differentiation, a gentle unfolding from unity to multiplicity. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes abstract ideas about symmetry and broken symmetry. Ponder the hidden elegance of fundamental laws, the quiet breaking of balance that gives rise to mass, the subtle asymmetry that allowed matter to triumph over antimatter, and the emergence of cosmic structures from primordial uniformity. Feel the quiet awe of existing in a cosmos where order and diversity arise from such elegant principles, inviting endless contemplation. There is a deep peace in this boundless mystery, in letting go of rigid demands for absolute perfection and embracing the universe's gentle, differentiated unfolding. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound narratives. Take another soft, peaceful breath now, allowing the elegant principles of symmetry and broken symmetry, those hidden orchestrators of reality, to settle gently within your mind. We've just explored how the very existence of mass and the structure of our cosmos arise from subtle acts of differentiation. Today, we will softly turn our gaze to a concept that challenges our intuitive grasp of reality, inviting us to consider a universe where the past, present, and future might coexist in a single, unchanging whole, the block universe. Imagine, for a moment, that time, as we experience it, is not a flowing river but a vast, frozen block of ice. We, with our consciousness, are merely skating across its surface, perceiving one moment after another as if they were unfolding anew, yet from a higher vantage point. The entire block, every moment from the very beginning of the universe to its ultimate end, exists simultaneously, eternally present. This is the profound and often unsettling concept of the block universe, also known as the eternalism theory of time. It's a whisper from the depths of physics and philosophy, suggesting a reality far more static and predetermined than our everyday experience implies. This idea emerges directly from Albert Einstein's special and general theories of relativity, which we touched upon earlier when discussing the nature of time. Remember, Einstein showed that time is not absolute but relative, intertwined with space into a four-dimensional fabric called space-time. The key insight is that observers moving at different speeds or in different gravitational fields will experience time differently. There is no single, universal now, if there is no absolute now that applies to everyone in the universe. Then the notion of a continually changing present, with a past that is gone and a future that is yet to be, begins to lose its foundational ground. Instead, in the block universe view, all moments in spacetime are equally real and equally existent. The past is simply a region of spacetime that has already happened, and the future is a region that has not yet been experienced by our consciousness. But it is just as real and fixed as the past. Think of it like a movie reel. When you watch a film, you experience it frame by frame. Sequentially, you feel like the story is unfolding in real time, but the entire movie, every frame from beginning to end, already exists on the reel. The future frames are just as real on the reel as the past ones. Our consciousness, in this analogy, is simply the projector's light, moving across the reel, illuminating one frame at a time. The events themselves are fixed within the block of space-time, existing eternally. This perspective can be deeply counterintuitive because our subjective experience of time is overwhelmingly that of a continuous, unidirectional flow. We remember the past, we act in the present, and we anticipate the future. We feel a profound sense of agency and free will, believing our choices can genuinely shape what is to come. The block universe gently challenges this intuition by suggesting that our perception of flow is an illusion, a trick of consciousness. One of the strongest arguments for the block universe comes from the concept of causality and spacetime intervals in relativity. In spacetime, events are connected by pathways. For example, if you send a light signal from one point to another, That light ray traces a path through spacetime for any two events. There is an invariant spacetime interval between them, a quantity that all observers, regardless of their motion, will agree upon. This mathematical rigidity suggests that all events are fixed points within this four-dimensional continuum. Rather than fleeting occurrences in a changing now, it's like a cosmic map where all locations are already marked. Even if we are only capable of visiting them sequentially, the implications of the block universe are profound and far-reaching. Determinism. If all events, past, present, and future, already exist and are fixed within the block, then it implies a highly deterministic universe. Our choices, our actions, our entire lives are, in a sense, already written into the fabric of spacetime. This raises deep philosophical questions about free will. If the future is already determined, do we truly have the freedom to choose, or are our decisions merely the unfolding of a pre-existing script? This is a quiet tension between the scientific description of reality and our profound subjective experience of agency. Know now. The block universe eliminates the idea of a universal now. What is now for you might be the past or future for someone else moving at a different speed or in a different gravitational field. This elegantly resolves the relativistic nature of simultaneity. There is no single moment that is simultaneous across the entire cosmos. Every event simply exists in its designated place within the space-time block. The nature of change. In a block universe, change is not about moments coming into existence and then passing away. Instead, change is merely the difference between different slices of the four-dimensional block. The apple that was green and then became red is not changing from green to red in a temporal sense. Rather, there is a green apple at time A slice of spacetime and a red apple at time B slice of spacetime, both eternally present within the block. It's a subtle but profound shift in how we conceptualize becoming and passing. This concept can be deeply unsettling for many, as it challenges our deepest intuitions about agency, choice, and the very flow of life. Yet, for others, the block universe can be a source of profound calm and acceptance. If the future is already there, existing in some sense, then there is a quiet reassurance that nothing is truly lost. Every cherished memory, every fleeting moment of joy, every whisper of love, every significant achievement, and every gentle act of kindness is not merely a fading echo from the past. Instead, it is an eternally existing, immutable point within the grand cosmic tapestry. It means that the loved ones we have lost are not truly gone, but simply exist in another part of the space-time block, always accessible in principle, always present in the greater reality. It offers a sense of profound permanence, a deep, unwavering stability to existence, the beauty of a sunset from 1,000 years ago, the quiet genius of an ancient philosopher, the laughter of a child in the distant future. All these moments are equally valid and equally real within the unchanging block. It's a cosmic comfort, suggesting that everything that ever was, is, or will be is eternally preserved, woven into the very fabric of reality. This perspective can also foster a deeper appreciation for the present moment. If every moment is eternally existent, then the now we inhabit is not merely fleeting, but a unique and precious point in the cosmic continuum. It encourages us to be fully present, to savor the gentle unfolding of experience, knowing that this very instant, once lived, is etched forever into the timeless canvas of space-time. While the block universe is a powerful interpretation of relativity, it is important to note that it is still a philosophical interpretation. Some physicists and philosophers argue for alternative views of time, such as presentism. Only the present is real, or growing block universe past and present are real. But the future is not yet fixed. The nature of time remains one of the most vibrant and debated areas of scientific and philosophical inquiry. Yet, the block universe hypothesis offers a compelling, elegant, and profoundly calming way to view existence, inviting us to transcend our limited, linear perception. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes unsettling ideas about the block universe. Ponder the notion that past, present, and future might coexist as a fixed cosmic block. Consider the implications for free will and the eternal preservation of every moment. Feel the quiet awe of existing in a cosmos where time is not just a flow, but an eternal landscape, inviting endless contemplation. There is a deep peace in this boundless mystery, in letting go of rigid demands for a singular, fleeting now and embracing the universe's gentle, timeless wholeness. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound narratives. Take another soft, peaceful breath now, allowing the profound stillness of the block universe, where all moments coexist eternally, to settle gently within your mind. We've just explored how time might not be a flowing river, but a fixed landscape, challenging our deepest intuitions about agency and change. Today, we will softly turn our gaze to a concept that feels intimately familiar, yet holds surprising depths of scientific and philosophical mystery. Color. Imagine, for a moment, the world around you, bathed in its vibrant hues, the deep blue of the sky, the soft green of leaves, the warm glow of a sunset. Color is such a fundamental part of our visual experience, shaping our perceptions, evoking emotions, and adding richness to every scene. But what is color? Fundamentally, is it an intrinsic property of the objects themselves, or something else entirely? A complex dance between light, matter, and our own consciousness. Our intuitive understanding often leads us to believe that a red apple is inherently red, or a blue sky is fundamentally blue. However, the universe, in its gentle complexity, often delights in revealing deeper, more interactive truths. The scientific understanding of color, as revealed by physics and biology, is far more nuanced and fascinating than a simple intrinsic property. Let's begin by recalling our journey into the nature of light. Remember that light is a form of electromagnetic radiation, traveling in waves. The different wavelengths of light determine its specific characteristics. The tiny portion of the electromagnetic spectrum that our human eyes can perceive is called visible light. And within this spectrum, different wavelengths correspond to different colors. For instance, longer wavelengths appear to us as red, while shorter wavelengths appear as violet, with all the colors of the rainbow in between. So, fundamentally, color is about the specific wavelengths of light. Now, how does an object acquire its color? It's not because the object inherently is that color, but because of how it interacts with light. When white light, which is composed of all the colors of the visible spectrum, shines on an object, the object's surface molecules selectively absorb certain wavelengths of light and reflect others. The color we perceive is the combination of wavelengths that the object reflects back to our eyes. Think of it like a silent conversation between light and matter. A red apple appears red because its skin absorbs most of the wavelengths of visible light, like blue. Green, yellow, and predominantly reflects the red wavelengths. A green leaf appears green because it absorbs red and blue light for photosynthesis and reflects the green wavelengths. A white object reflects almost all wavelengths of visible light, while a black object absorbs almost all wavelengths. So, an object's color is not a fixed property, but a dynamic, constant interaction with the light that falls upon it. If you were to shine only blue light on a red apple, it would appear black, because there's no red light for it to reflect. It's a gentle reminder that our perception of color is utterly dependent on the presence and interaction of light. But the story of color doesn't end with physics and the interaction of light with matter. It extends into the realm of biology and consciousness. The reflected light then enters our eyes, specifically hitting the retina at the back of our eye. The retina contains specialized light-sensitive cells called photoreceptors rods and cones. Rods are responsible for vision in low light, while cones are responsible for color vision. Humans typically have three types of cones, each sensitive to different ranges of wavelengths roughly corresponding to red, green, and blue light. Our brain then takes the signals from these three types of cones and interprets them as the vast spectrum of colors we perceive. It's a remarkable feat of neural processing, combining these primary signals to create the rich, nuanced hues of our visual world. This means that color, in its purest sense, is not out there in the world. It is a subjective experience created within our brains. The light waves are external, but the feeling of redness or blueness is an internal, conscious interpretation. This distinction is profound. Two individuals might be looking at the exact same wavelengths of light reflecting from an object, but their subjective experience of color could be subtly different, influenced by their individual biology, their unique brain processing, and even their personal associations and memories. This is why the hard problem of consciousness, which we explored earlier, is so relevant to understanding color. How does the physical stimulation of cones and neurons give rise to the rich, qualitative experience of seeing a vibrant yellow? Consider the implications of this subjective nature. Animals, for instance, often perceive color differently from humans. Bees can see ultraviolet light, which is invisible to us, but they cannot see red. Dogs have only two types of cones, making their color perception more limited than ours. This means that a flower that appears a certain color to us might appear entirely different to a bee. Revealing hidden patterns that guide it to nectar, it's a gentle reminder that our shared reality is filtered and interpreted by our unique sensory apparatus. And there are many different ways to see the world. The contemplation of color, therefore, takes us on a journey from the fundamental physics of light through the intricate biology of our eyes, and ultimately into the mysterious realm of consciousness. It reveals that what we often take for granted as a simple, objective property of the world is, in fact, a complex dynamic interplay of light, matter, and mind. It's a constant, silent conversation happening in every moment of our waking lives. This can be deeply calming. It invites us to appreciate the subtle magic in everyday perception, the vibrant beauty of a rainbow, the delicate gradient of a sunset, the rich tapestry of a garden. These are not just external phenomena, but co-creations, woven by the interaction of cosmic light with earthly matter and our own inner awareness. It suggests that our subjective experience is not separate from the universe, but an active participant in its unfolding. It also reminds us of the hidden layers of reality, just as color emerges from the interaction of light and matter. Perhaps other seemingly objective properties of the world are also subtle, complex interpretations that our consciousness constructs. It encourages us to approach all perceptions with a quiet curiosity, understanding that the universe is always ready to reveal deeper, more interactive truths. The colors of the world are a gentle, luminous whisper, inviting us to look closer, to feel deeper, and to wonder at the intricate dance of reality. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes counterintuitive ideas about color. Ponder its essence as a specific wavelength of light, its dynamic interaction with matter, and its ultimate subjective creation within our consciousness. Feel the quiet awe of existing in a cosmos where the visual richness of our world is a co-creation, a beautiful symphony of light, biology, and mind, inviting endless contemplation. There is a deep peace in this boundless mystery, in letting go of rigid definitions of what is seen and embracing the universe's gentle, luminous dance. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound narratives. Take another soft, peaceful breath now, allowing the vibrant, subjective nature of color that intricate dance of light, matter, and consciousness. To settle gently within your mind, we've just explored how our visual world is a co-creation, a beautiful symphony of interactions. Today, we will softly turn our gaze to a concept that challenges our very notions of what is fundamental, inviting us to consider the profound role of information. Imagine, for a moment, that everything we perceive, every particle, every force, every thought, every memory is, at its deepest level, a form of information. This isn't just about data stored on a computer. It's the radical idea that information might be more fundamental than matter or energy. That the universe itself is, in some profound sense, a cosmic computation, or a vast, intricate pattern of bits. It's a whisper from the cutting edge of physics and philosophy, suggesting that reality might be more abstract and interconnected than our senses typically reveal. For centuries, our understanding of the universe has been built upon the bedrock of matter and energy. We believed these were the fundamental constituents, and information was merely a property of matter and energy. But the universe, in its gentle complexity, often delights in revealing deeper, more foundational truths. The idea of information as fundamental began to gain traction with the rise of quantum mechanics and black hole thermodynamics. Quantum mechanics and the bit in the quantum realm. Particles don't have definite properties until they are observed or measured, as we explored with matter and color. A particle exists as a blur of possibilities, a probability wave, until an interaction collapses it into a definite state. This act of measurement extracts information from the quantum system. It's as if the universe is constantly processing information, resolving uncertainties into definite bits of reality. This has led some physicists, like John Archibald Wheeler, to propose the radical idea of it from bit, the notion that every particle, every field, every law of physics ultimately derives its existence and meaning from bits information. It implies that reality isn't fundamentally made of tiny particles, but of questions answered, choices made, or information defined. Black holes and information loss. Black holes, as we gently explored, pose a profound challenge to the idea of information conservation. When matter falls into a black hole, it seems to disappear forever, along with all its information. Yet, quantum mechanics insists that information can never be truly destroyed. This information paradox has led to intense debate and fascinating theories, such as the idea that information is subtly encoded on the event horizon of a black hole, like a cosmic hologram. If this is true, it means that information is so fundamental that even the most extreme gravitational environments cannot truly erase it. It is merely transformed or re-encoded. This suggests that information is not merely a consequence of matter, but perhaps a more enduring, pervasive aspect of reality itself. This perspective implies that the universe might be fundamentally digital or informational at its core. It's not that the universe is a computer program in the way we write code, but rather that its underlying structure and processes can be best understood through the lens of information theory. Every interaction, every particle state, every cosmic event can be seen as a transfer or processing of information. Think of it like this. Imagine a vast, intricately woven tapestry. We might focus on the threads, matter, ice, energy, or the colors light. But the deeper truth is in the pattern, the information that defines the tapestry as a whole. The universe, in this view, is a grand, evolving pattern of information, constantly being written and rewritten. The concept of information as fundamental also touches upon several other profound ideas we've explored. Entropy. Entropy, the measure of disorder, can also be understood as a measure of missing or unavailable information about a system. As entropy increases, information becomes more spread out and less accessible. The universe's journey towards higher entropy is, in a sense, a journey towards a state where information is maximally dispersed, consciousness. If information is fundamental, then consciousness itself might be a highly complex form of information processing, or perhaps even a fundamental, irreducible form of information exchange. The subjective experience of being could be the universe's way of processing its own information. It asks if our thoughts are not merely products of brain chemistry, but patterns of information unfolding within the cosmic fabric. The multiverse. In some multiverse theories, especially the mathematical universe hypothesis, the idea is that all mathematically consistent structures exist. If physical laws are essentially information structures, then the multiverse could be seen as an infinite library of all possible informational universes. This informational perspective is still a deeply philosophical and theoretical realm, but it opens up astounding possibilities for understanding the universe. It shifts our focus from merely what is it made of to what does it know or process, Moned. It invites us to consider that reality might be less like solid stuff and more like a dynamic, self-organizing pattern of relationships and possibilities. The implications are far-reaching. If information is truly fundamental, it might suggest that even what we perceive as empty space or nothingness, the quantum vacuum, is not devoid of information. Instead, it might be a sea of potential information, constantly fluctuating and giving rise to the bits that constitute our reality. This can be deeply calming if information is conserved. Even after a particle has vanished into a black hole or transformed into energy, then there is a profound sense of continuity in the universe. Nothing is ever truly lost, merely transformed or re-encoded. It suggests that every experience, every thought, every interaction leaves an indelible informational trace, woven into the eternal tapestry of the cosmos. It also encourages us to see ourselves not just as collections of matter, but as intricate, luminous patterns of information, constantly exchanging and processing knowledge about the universe, our consciousness, our memories, our very identity, are profound manifestations of information in action. There is a deep peace in realizing that we are not separate from this cosmic flow of information, but active participants in its continuous unfolding. We are, in a sense, the universe's way of observing and processing itself, a tiny, self-aware piece of the grand informational pattern. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes abstract ideas about information as fundamental. Ponder the it from bit concept, the information paradox of black holes, and the universe as a vast, unfolding pattern. Feel the quiet awe of existing in a cosmos where reality itself might be composed of something as elusive yet pervasive as information. Inviting endless contemplation. There is a deep peace in this boundless mystery, in letting go of rigid definitions of stuff and embracing the universe's gentle, informational dance. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence. Welcome back, gentle friend, to our quiet journey through the universe's most profound narratives. Take another soft, peaceful breath now, allowing the radical idea of information as fundamental, that the cosmos itself might be a vast, intricate pattern of bits, to settle gently within your mind. We've just explored how reality might be more abstract and interconnected than we usually perceive. Today, we will softly turn our gaze to a concept that feels deeply personal, yet also profoundly universal: the nature of reality itself. Imagine, for a moment, questioning everything you take for granted about what is real: the solidity of the ground beneath your feet, the warmth of the sun, the laughter of a loved one. These all feel undeniably real. But what if reality is not as straightforward as it seems? What if it's not merely a collection of objective things out there, but something more fluid, more interpretive, or even a continuous co-creation between the universe and our consciousness? This is the profound and captivating inquiry into the nature of reality, a whisper from the deepest philosophical and scientific frontiers, inviting us to look beyond the surface of existence. Our journey through the cosmos has already unveiled several layers of surprising complexity that challenge our intuitive grasp of reality, the elusive nature of matter. We've seen that matter, at its most fundamental quantum level, isn't solid billiard balls but rather fuzzy probability waves that only collapse into definite particles upon observation. This implies that reality isn't just there, independently of us. Our very act of observing seems to play a role in defining its definite form. It suggests that reality is not entirely objective, but has a subtle, participatory aspect, the flexibility of time and space. Einstein's relativity showed us that time isn't absolute but relative, woven with space into a dynamic space-time fabric that can be warped by mass and energy. The concept of the block universe further suggests that past, present, and future might coexist eternally, challenging our linear perception of time's flow. This means that the stage of reality itself is far from fixed, bending and shifting with cosmic influences, the hidden universe. We've encountered dark matter and dark energy, invisible components that constitute the vast majority of our universe, yet remain entirely beyond our direct perception. This tells us that most of what exists is unseen, unheard, untouchable, profoundly different from the reality our senses are built to experience. Our perceived reality is merely a tiny fraction of the whole, the quantum vacuum's vibrant emptiness. What we once thought of as empty space, the quantum vacuum, is in fact a teeming sea of virtual particles, constantly flickering into and out of existence. This challenges our notion of nothingness and suggests that even the void is pregnant with potential, a vibrant, energetic canvas from which reality might emerge. The informational universe. The idea that information might be more fundamental than matter or energy suggests that reality is not about stuff, but about patterns, relationships, and bits of data. This implies a universe that might be akin to a cosmic computation, or a vast, unfolding algorithm, where every interaction is a processing of information, taken together. These scientific discoveries paint a picture of reality that is far more mysterious and dynamic than our everyday experience suggests. It's a universe of probabilities, interconnections, hidden dimensions, and unseen forces. This prompts a deeper philosophical inquiry. Is reality objective? Existing independently of any observer, with a single definitive truth waiting to be discovered? Or is it, to some degree, subjective, shaped by our consciousness, our perceptions, and our interpretations? Most scientific inquiry operates under the assumption of an objective reality, seeking universal laws that apply to everyone, everywhere. This approach has led to incredible breakthroughs and our current understanding of the cosmos. However, the quantum realm gently pushes us towards a more nuanced view, where the act of observation seems inextricably linked to the manifestation of reality. Consider the idea of constructivism. Particularly relevant to our understanding of consciousness and color, we don't just passively receive reality, our brains actively construct our experience of it. The sensation of color, the perception of a coherent image, the interpretation of sounds, these are all intricate processes occurring within our minds. This suggests that while there may be an external reality, our experience of that reality is a unique construction, filtered through our senses and interpreted by our consciousness. This leads to even more profound questions. Is reality a simulation? This mind-bending hypothesis suggests that our entire universe, including our consciousness, might be a highly advanced computer simulation if reality is fundamentally informational, as some theories suggest. Then such a simulation might be indistinguishable from base reality. It's a speculative thought, but one that encourages us to question the very fabric of our perceived existence. Is reality fundamentally mental or conscious? Pushing the idea of panpsychism even further, some philosophical views propose that consciousness or mind is the ultimate, fundamental reality, and that matter and energy are emergent properties of this underlying awareness. In this view, the universe is not merely observed by consciousness, it is consciousness. in some profound, all-encompassing way. This perspective offers a deeply spiritual connection to the cosmos, suggesting that our individual awareness is a facet of a universal mind. These various perspectives, scientific, philosophical, and even spiritual, are not necessarily mutually exclusive. They represent different levels of inquiry, different languages attempting to describe the same profound mystery. The beauty lies in their quiet convergence, hinting at a reality that is both rigorously physical and deeply conscious. Both objectively structured and subjectively experienced, the contemplation of the nature of reality can be deeply calming. It invites us to release rigid certainties and embrace the boundless possibilities of existence. If reality is more fluid and participatory than we imagined, then our role within it becomes even more significant. Our thoughts, our intentions, our very way of perceiving might subtly contribute to the continuous unfolding of the cosmic story. There is a profound peace in the gentle acceptance that the universe is far stranger and more miraculous than we can ever fully grasp. It reminds us that knowledge is an endless journey, a continuous unveiling of deeper and deeper layers of truth. We are not just living in reality in some profound sense. We are also actively, gently, bringing it into being through our very awareness. This shared mystery, this boundless potential, connects us all. As we gently conclude this chapter, allow your mind to drift with these profound and sometimes unsettling ideas about the nature of reality. Ponder its elusive objectivity, its participatory quantum dance, its hidden dimensions, and its potential as a grand simulation or universal consciousness. Feel the quiet awe of existing in a cosmos where the very definition of real is a source of endless wonder and inquiry, inviting boundless contemplation. There is a deep peace in this boundless mystery, in letting go of rigid demands for simplistic answers and embracing the universe's gentle, multifaceted, and ever-unfolding truth. Let these thoughts carry you further into a state of profound tranquility, a peaceful surrender to the endless wonder of existence.